this is the first time that we organize an Equivariance workshop explicitly for a vision audience. And we are really super excited about this opportunity to bring you both foundations of Equivariance and applications in a one-day event. The workshop has been organized, and the leading organizers were Chongyue and Yin Shuang, and I see also, among others, Vitor here, and I don't know who else is already here. But yeah, thank you very much, and I will thank you again at the end of the workshop. So we feature, this is not a workshop with just invited talks. We have we have 5 wonderful invited talks, starting with Haggai and Leo Gibas, Carlos, Nina, and Eric Becker. We have a tutorial, which is really for getting started with Equivariant networks, even if you haven't heard anything ever about the Equivariant networks. And we have 4 spotlights and a quite long series of posters. The history of equivariance is quite long. Obviously, the definition comes from the mathematics, from equivariant maths, from equivariant maps. But the first time that it appears quite explicitly in the pattern recognition community is by Shunichi Amari in ICPR 78. This is the same Amari that also has been publishing in information geometry and a lot of, there is also a whole conference that he organized on information geometry. And then even in the 90s, there were several efforts, among them from the dissertation of Patrick Theo at Stanford, where they were trying to build equivariant and steerable, actually, functions by handcrafted networks, not neural networks. Coming back to today, today we have equivariance has been applied widely in the sciences, in computational chemistry, in biology, and even in vision, where we have in the main conference, we have several papers spanning from descriptors and in the 3D point clouds and even like image reconstruction. It is a quite exciting field, even if what we realized lately, and I think also Nina will talk about it, is that even if we discover that filters by themselves become equivariant during the learning process, we weren't be able to recognize that for transformations beyond the translation if we hadn't studied all the mathematics behind both equivariant kernels and equivariant nonlinearities. In general, while data augmentation has been the way to go, it is quite expensive and does not provide that insight when we build a system. So I'm gonna just finish with a very old meme. This is from the Matrix ping pong. When the movie The Matrix came out, there were several efforts to mimic it. And this is a way to make data augmentation work in 3D, and you're gonna see how expensive it is. If you see the makeup, actually, there are all these people in black actually turning these people in order to really mimic novel viewpoints of the scene, which you cannot always get by just having a dome of cameras around it. And there were several actually memes, and there was also a whole line of theater plays in Japan using these techniques. while you are still watching this, I think we are going to start setting up Hagai's talk, and Chong will run also will introduce Hagai, right? All right, thank you for joining us today, and I urge you to stay for the whole day up to the tutorial, which will be between 4 and 5 p.m.
Oh yeah, hello Hagai, can you hear me?
Yeah, I can hear you well. Can you hear me?
Oh wait, sorry. Sorry, can you speak again?
Yeah, can you hear me now?
It seems that. Wait.
Use a speakerphone.
Oh, I see. Yes. Thank you so much. Is this it? Sorry, Hagai, would you mind speaking again?
Yeah, can you hear me now?
Oh yeah, great, yeah. Yeah, we can hear you
Amazing.
now. Yeah, thank you so much, and sorry for the confusion.
Sure. Can you see my screen?
Yeah, we can see it here.
Great.
Yeah, we just had an introduction to you, and sorry because of the audio issue, probably you didn't hear that.
Oh, no worries. So I can start.
Yeah, feel free to get started when you're ready, and thank you so much for delivering this talk at this workshop.
Sure, and thank you so much for inviting me. This is a real pleasure to talk here in this workshop, and I'm so sorry I cannot be there in person. Hopefully next time. So my name is Hagai. I'm an assistant professor at the Technion and a research scientist at NVIDIA. And I'm going to talk about symmetries for learning in deep weight spaces, which is a recent topic my group and colleagues are working on recently, which I find very interesting. and I'll try to convince you as well. So this is the outline of today's talk. We will start with a brief intro to symmetries and equivariant networks. Hopefully this will take only a few minutes, and then we will talk about learning in weight spaces, what exactly this means, what is the setup. We will see two methods for learning in weight spaces. The first one using linear equivariant layers. The second one is using graph meta networks. And then we will conclude with a few very recent papers we are going to present at ICML next month with new directions in this topic. Okay, so we'll start with deep learning with symmetries, and we are going to focus specifically on permutation symmetries, and this will become clear in a sec. So in general, many structured objects have symmetries. And when I say symmetries, I mean transformations that keep the properties of an object unchanged. So the usual example is to think about images and then to think about translation. And then translations do not really change the essence of the object, right? The image. And in many, many cases, learning tasks that we are interested in are invariant to those kind of transformations. And again, the prototypical example is image classification. And the main idea, the way I see it behind this field, is to leverage those symmetries that we have in the input domain in order to construct efficient learning models. And the principle, maybe a bit more directly, is to restrict the hypothesis class that we are learning on to models that respect the symmetries that we have. So for example, use invariant models for invariant tasks. And we know that there are several benefits to that. First of all, on a broader sense, it injects a very good prior knowledge to the model about the problem that we are trying to solve. But we can also show that you get better generalization and that the networks themselves have less parameters and are more efficient. So we turn to permutation symmetries. Permutation symmetries are symmetries that can be described by subgroups of the symmetric group Sn. Of course, not all symmetries fall into this category, but this is quite general. So for example, translations in images, one can think about them as a certain very specific subset of translation of permutations to the pixels, right? So this falls into the category of permutation symmetries. Also, point cloud symmetries. Assume that you have a point cloud, which is an n/3 matrix. Then changing the order of the points in the point cloud doesn't change the point cloud. So in this case, the symmetry group is the group of row permutations in this case. And this is another example of a subset of the full permutation group that we can use as a symmetry group. Invariance means that for any transformation in my symmetry group, applying the transformation to the input doesn't change the output. And again, image classification is a good example for that. If we apply tau, the transformation, and then apply f, we get exactly the same thing. Equivariance is a generalization of that idea. Essentially, equivariance means that the function and the transformation commute. And this can be seen nicely in this commutative diagram here. We have a cat. Here we move it, then we apply f and get some other function, but it doesn't really matter if I first apply f and translate, or first translate and then apply f. And essentially, we all know equivariant functions from convolutions, right? Convolutions are exactly the set of all translation equivariant linear functions. So very central question in this field is, given a group G acting on our data, how can we design an invariant or equivariant neural network for this data type and this symmetry? And perhaps the most popular approach is to compose several simple equivariant layers. And this approach just follows the idea that we used in CNNs for all these years. Essentially, you use a linear equivariant layer, and on top of that, you use a pointwise nonlinearity. In the case of images, those linear equivariant layers are just convolutions. In case that the problem we want to solve is invariant and not equivariant, we can have a pooling layer on top of that, and then run any fully connected network. And now the question is, how can we come up with those simple equivariant layers? So there is a nice recipe for that. If we restrict ourselves to only affine layers, Wx plus B, and a pointwise nonlinearity on top of them, then a nice result shows that if the layer defined by W essentially is equivariant if and only if it has a very specific parameter sharing scheme defined by the group. So in other words, if I can move ij to kl by a group element, then those two entries in the matrix should have the same parameter. And this has been known for quite some time. Let me give you a few examples for that. For 2D translations, for example, we will get just the convolution matrix, which we see on the left side here. For the very nice case of set permutations, where we don't really care about the order of the elements in the set, we have PointNet and deep sets, two very exciting papers from 7 years ago that showed how those layers should look like. And when we have no symmetries, we have no parameter sharing scheme, right? So each one of the entries has a different parameter, and this is a fully connected network. And we used this approach in the past few years in order to come up with equivariant networks for all sorts of data types that we encounter in practice. So for example, on the left side, we can see graph permutations. So it's again the symmetric group, but acting differently on graphs by conjugation. On the right side, we have sets of elements with their own symmetry. In this case, we have sets of elements where each element has cyclic symmetry. Okay, and a key challenge when constructing those kind of neural networks is understanding their expressive power. Essentially, we are restricting our hypothesis space to a specific subset of functions, and we are interested in understanding whether there is a gap between the invariant networks that we can approximate and all the G-invariant continuous functions. Okay, so to recap, if we are interested in invariant tasks, it is beneficial to use invariant models. In the case of, in any case, those can be constructed from equivariant layers. And in the case of permutation symmetries, we have a very nice recipe for constructing those equivariant layers by parameter sharing governed by the group action, essentially. So this was my kind of starting point for equivariance. And now I would like to move on to our recent work on learning on deep weight spaces. So this work was led by three amazing students, Aviv Shamsian, Aviv Navon, and Idan Achituv, and other people. So essentially, we know that neural networks are a very good model for learning from data. for example, CNNs and LLMs and any other neural network that we train in order to predict something on an input data point. And recently, neural networks also became a primary model for representing data samples themselves. So what I mean here is implicit neural representations. Essentially, neural networks can be used in order to represent images, 3D shapes, and even scenes, as we will see shortly. The idea is that the neural network takes as input a pair x, y of coordinates and outputs the RGB value corresponding to this position in the image. If we train the neural network to predict the correct RGB value for each x, y, then we essentially encode the image inside this neural network. This is, in many cases, an MLP, a fully connected network. And then, essentially, the weights of this MLP represent the image. Another example is nerves, neural radiance fields, which allow us to do something similar, but on the whole scene and not only on an image or a 3D object. So the situation now is that there are very large collections of trained networks online. So for example, on Hugging Face alone, there are over 600,000 models. When we start having NERF and INR data sets online, and we are going to ask two questions here. So the first is, does it make sense to apply machine learning to these neural network collections? Is it useful for us, or it's not? And the second question is that in case the answer is positive, what is a good way to do that? So how to apply machine learning to neural networks as inputs, right? Those are the two questions. So in order to give you some motivation, what we can do with those kind of networks, I will try to give you two motivations. The first one is for processing INRs. So in this part of the figure, we see INR training procedure in which we train the INR to represent the figure 5 from MNIST here. And below, we can see us taking the weights of the INR and pushing them into a neural network, trying to predict the class. Okay, so we might want to perform classification tasks on INRs, right? And INRs are naturally represented as weight vectors. So we need neural networks that can work on weight vectors. This is not only restricted to a classification. We can think about editing INRs, generating INRs, and so on. Essentially, those weight vectors are becoming a new data modality, and we need to understand how to apply machine learning to it. The second motivation is about processing more general networks. So think about a case in which we would like to take as input some network and to get as output some altered version of this network. Think about pruning a neural network, binarizing it, predicting, making it more robust or stuff like that. It would be extremely nice if we could train a neural network to do all this stuff. So essentially, after training such a neural network, we can take an input model and push it through this special neural network that we are going to discuss, and then get another neural network that has the properties that we want. In this particular case, we perform domain adaptation. So we take some network trained on CIFAR10, and then we adapt it by mapping it through a neural network to a different data set. And now the challenge is, what is a good architecture for learning on neural networks? And this will be the main topic of today's talk. So let's try to formulate it a bit. First, we focus in this talk on MLPs. All things here can be extended to other types of models. So MLPs are just sequential models that apply linear layers and pointwise nonlinearities, as we all know. And for us, an MLP is represented by its weights and biases. So think about this vector concatenation of all the weights and all the biases. And when we say we process an MLP, what we actually mean is that we apply a function to its parameters. So essentially, this is the idea. We take a neural network represented by W1, W2, W3, and so on. We push it into a network of function f, and then we output new parameters. And this is a different neural network now. Okay, so what would be the most naive or first solution we can try to solve this problem? We can try to vectorize all the weights in a single very long vector and then apply the most simple networks that we can think about, essentially a fully connected network. So this was done and was successful to some extent, but it has several limitations. And those are the natural limitations that we always see when we don't use the correct neural network for our data type or for the symmetry type. So we get huge parameter space. For example, for a neural network that has like 100K parameters, every linear layer would be 100K squared. So this is a huge number of parameters. Second thing is that we totally ignore the structure of the weight space. And we know that structure can be used in order to come up with better models. And essentially a better approach, which we suggested in an ICML paper last year, is to take into account the weight space symmetries. So again, just to make sure we are on the same page, for images, we know that we have translation symmetries and we use CNNs. For point clouds, we know that we have permutation symmetries and we use deep sets or point nets, or now transformers, for example. And the question in our case is, if the input is a deep network represented by its weights, what should be our model? And what are the symmetries? Okay, so specifically in our case, in the case of images, we have arrays of pixels as input. The symmetry group is 2D cyclic translations. The basic layers are 2D convolutions. And the resulting architectures are the CNNs we all know and love. In our case, we know that the input is the weights and the biases of the MLPs, but it remains unclear what are the symmetries, what are the basic layers, and what do we get as the architecture. And also, I would add, what can this architecture do in terms of expressive power? So we should start from the symmetries. And the symmetries in the weight space case are extremely interesting and cool, I think. So the idea is that we can switch any two neurons in an intermediate layer, and we will get exactly the same function, right? The order of those neurons doesn't really matter for us. Only the order in the input layer and in the output layer. Algebraically, what we see is that we can apply any permutation matrix and then compensate in the next layer by the inverse permutation matrix. So those two permutations, when we apply the linear layers, they cancel each other, and then we get exactly the same function. And this, of course, trivially extends to even deeper networks. So those are the symmetries we are interested in. I should say that there are other symmetries as well, like scaling symmetries. For example, we can apply some scaling before a nonlinearity and after a nonlinearity, and then compensate on that. This is something that we are not going to tackle in this talk, but there are some works that try to tackle that now. So we know what are the symmetries, and according to the scheme that we discussed, we need to construct simple equivariant layers. And the idea is to characterize all the equivariant, linear equivariant layers for those kind of symmetries. This is what we are going to do now. Essentially, what we are going to show is that the layers follow a natural block structure, and each block maps between specific weights and bias spaces. And those blocks are essentially very simple. They can all be implemented by broadcasting, pooling, or very small fully connected layers. Those architectures are called DWS networks, for deep weight space networks. So the main observation driving our characterization is the following. The weight space is a concatenation of all the weights and the biases. And the symmetry group acts on each one of those independently. This means that if I have W1 here and I apply a group element, all the entries of W1 will end up here. The same is true for all the biases and all the other weight matrices. We can see that pretty clearly from this equation, right? W1 moves to a permutation of W1. W2 moves to a permutation of W2, and so on. In more formal terms, this is called the direct sum of representations of the group. Essentially, a concatenation of several vector spaces on which the group acts independently. And this gives us a nice structure to work with. So a very simple result in group representation theory states the following. If we have an equivariant map between a concatenation of two vector spaces, V1 and V2, and to another concatenation on which the group acts independently, then we can actually break this linear equivariant map into 4 different blocks, and each one of them is going to be an equivariant layer between the respective representations. So as we see here, we have a map between V1 plus V2 to V1 prime plus V2 prime. And if we look on this square, we can see that this is a map between V1 to V1 prime. And this helps us a lot. Essentially, this is a decomposition theorem that allows us to take this huge problem and to break it into several very small problems. And let's see how we exactly use it. So the first use case is to take the whole weight space and to break it into 4 different linear maps. The weight map, mapping between all the weights to all the other weights, the bias weight map that maps biases to weights, and so on. So we took our problem and broke it into 4 smaller problems. And now we are going to use this decomposition again to show that each one of those blocks decomposes again into a block structure where each one of the blocks maps between a specific weight matrix and a specific weight or bias matrix. So for example, this block maps between WM, the last weight space, weight matrix, and W1, and so on. Different colors here represent different types of mappings. But as we said, all of them are more or less variations of deep sets and point net. So those are very simple things. Maybe in a bit more detail, if we look closer and zoom into a specific a row of blocks here, we can see that we have a self-update rule, which essentially updates the mth weight matrix by itself. This uses an equivariant layer characterized by Hartford et al. From ICML 2018. And essentially, this is a tensor product of deep sets or point net with itself. Here we have deep sets. This is just simple summation, and this is another variation of deep sets. So essentially, breaking down all this block matrix structure gives us a list of very simple equivariant layers we need to implement. As we discussed before, equivariant layers architectures might not be expressive enough. This is, for example, a common problem in GNNs. So we have two theoretical results on this matter. So I will state them very informally, but I'm happy to talk about it later if someone wants. I'm available online or on email. So essentially, DWS networks are capable of approximating feed-forward operations on their inputs. What that means is that if I give the weight space network a set of weights and an input to the input network, there are weights for the DWS networks that will give me the application of this input MLP on this input X. You can think about it as something that is similar to a universal Turing machine or something like that. The DWS networks can learn to think about the inputs not as weight vectors, but as functions. And using this result, we show that DWS networks can approximate any nice function, which I will not exactly define here, but it's a preliminary result for expressive power of DWS nets on the space of functions on MLPs. I believe there is a lot of work to be done in this direction of understanding the expressive power of those methods. We turn to some experiments. So the first experiment is very simple. It's an INR classification experiment. So again, as we saw before, we are training 70,000 INRs on MNIST, each one representing some digit. And then we train a DWS network to take those weights of the INRs as input and to predict the correct class. So let's see what are the results. First of all, applying an MLP doesn't work well. And this is something that we could have imagined before. We know that an MLP wouldn't work well in this case because it doesn't take the structure into account. The second row here, third, sorry, shows MLP plus alignment. So essentially, we run a procedure before training to align all the networks together. So kind of find the optimal permutations between the neurons so they all live in the same space. This is an NP-hard problem, so we had to use some approximation algorithm in order to do that, which runs a long time. And we see that MLP plus alignment works pretty well, much better than MLP alone or MLP plus augmentations. Our networks perform even better than that, and by a wide margin. And we do that without solving any NP-hard problem, without pre-processing and anything like that. All we need to do is to use the correct DWS, the correct network and layer architecture for the data type that we have. So we consider this a pretty good result. I'm sure that all of you now think that 85% on MNIST is not so good. This was the first result we had on that, and the results now are much better. And we will talk a bit later in this talk on how to improve the results here. But the main thing to take here as a message is the very wide margin we have from other approaches. This is another experiment that I like to do when designing equivariant networks. And essentially what we try to do here is to understand how the sample complexity of those models behaves. So on the y-axis here, we have the error of a specific task that we trained on. And on the x-axis, we have the number of samples we used for training. And so what we see here is how well a model generalizes according to the amount of data that it uses. And you can see the very large difference between DWS networks here and all the other approaches. You can see that it might take forever for us essentially to get to a good place with MLP plus alignment, but we already solved the problem pretty well with 800 samples in this case, if we use the correct equivariance structure. So we are not the only ones that worked on this direction, and there are three very nice works by Ellen Zhu from Stanford, and I encourage everyone to look at these works as well. They came out in parallel to our works and do stuff in a similar way, although there are some differences. So what are the limitations of our approach? First of all, the architecture is tailored for a specific MLP architecture. So an MLP with K layers and I don't know, 128 neurons. If I want to apply these networks that I trained on specific architecture to another architecture, I cannot do that because the architecture is tailored to a specific weight space. Second thing is that, well, while I try to convince you guys that everything is very nice and elegant mathematically, it involves very long derivations and the implementation can be challenging a bit. And also, it is quite difficult to modify and apply design choices. So for example, if I want to add an attention mechanism, for example, and if I want to add a normalization there, everything needs to be derived for the specific architecture that we are using. So in the next work from iClear this year, we are going to talk how to alleviate those problems. And this work is called Graph Neural Networks for Learning in Deep Weight Spaces. It was led by Derek Lim from MIT and James Lucas from NVIDIA. And essentially, the main idea is very natural. It says the following. A neural network is essentially a graph. How can we construct this graph? Well, the inputs are the input nodes in this graph. Each one of the neurons is a specific node. The biases are going to be another node. And we are going to have edges between neurons that are connected to each other. And on those edges, we are going to encode the weights, right? So this is just the weight between the first input and the first neuron here. Essentially, all the weights are encoded in this graph on the edges. So a good question now would be, what are the symmetries in this case? And the idea is that we can design the graph such that any automorphism of the graph, such as the ones that we see here, preserve the neural network function. So in that case, we have a bunch of permutations on the nodes of the graph that will be our symmetries. The good thing about it is that we know how to be equivariant to permutations on graphs. We can just use a graph neural network. And this is exactly what we did. So we use a GNN to process the graph generated by the weights and the MLP architecture. And those GNNs will be naturally equivariant to those automorphisms. So why is that a good idea? I'm going to say three things. First, one GNN can process different architectures, different sizes, anything, because our GNN can process any graph. So as long as you can encode or describe an input architecture as a graph, you can apply the GNN to it. And this is great. This is something that we couldn't do before. And in the paper, we show how to build graphs for many types of gadgets and architectures that are frequently used in deep learning. So for example, attention layers, convolutions, and normalization layers, and so on. The second advantage is that by moving to this model, we don't lose expressive power. So we can show that on MLPs, those graph metanets can simulate other weight space networks and can also simulate forward passes like we discussed in the previous model. The last advantage, which I think is very significant, is the fact that we inherit a very large body of work on GNNs. What I mean by that is that essentially I can take any off-the-shelf GNN. It can be a graph transformer, it can be a message passing neural network, it can be an expressive model, anything you want, and you can apply that to this task. And by doing that, you can use all the knowledge that the graph learning community has gathered until now, all the different attention normalization ways, to positional encodings, all the different stuff that people did on graphs are applicable to weight spaces now. So in parallel to this work, another work by Kofinas et al. From the University of Amsterdam did something very similar to that. So yeah, I encourage you to take a look on this work as well. And now we turn to the last part of our talk. I'm going to discuss two recent papers that got accepted to ICML in which we used weight space networks. So the first paper tries to learn to align weight spaces. And the motivation is for merging models. So merging models is a very interesting problem. The idea is that we want to take two models. Let's assume now that they have the same architecture, and we would like to create a new model that will have the benefits of those two models, for example. And one generic way to merge models is by first performing weight alignment. So weight alignment is the process of finding the group element that makes the weight vectors as similar as possible. This G here that we see, it's a concatenation of permutations for all the layers. And it is applied to this W in the way that we saw by the permutation matrices before. So our idea is to first align the weight vectors and then to perform some convex combination on top of them in order to merge the models. The problem is that this weight alignment problem is NP hard, as we already mentioned. So in line with a large body of work that tries to learn how to solve NP hard problems on specific data distributions, we try to learn how to solve this weight alignment problem. And again, key to the solution here is understanding the symmetry structure that we have in the problem. So let's try to understand what we have here. Here we have two neural networks represented by two vectors, weight vectors, V and V prime, each one with its own matrices. And our task is to find the optimal permutations for the alignment. So this is some function, maybe it's hard to compute it, but there is some function that takes me to the optimal permutation. What are the symmetries of this problem. So let's say that I apply permutations to both the weight vectors. So I can apply some permutation P1 and P2 to the first network, and some permutations P1 prime and P2 prime to the second one. What we can show in the paper is that the output permutations will undergo a similar transformation. So essentially, we have a very similar but different symmetry structure to the one that we described before in the previous papers. In order to solve the problem, we devise a new architecture that uses DWS networks and predicts those optimal matrices, hopefully optimal matrices. And we show this works pretty well. We have multiple experiments showing the benefits of using that in many cases, for example, in federated averaging, for example. So if you're interested in federated learning, take a look. The second problem or paper that I want to talk about is about data augmentation in weight spaces. So what we saw in the year or so that we are working on that, year and a half, that weight space architectures suffer from severe overfitting. The problem is that generating data for weight space learning is hard, right? We have to train each example. Thing is that we tried to do that, to come up with very much larger data sets, and we saw that the overfitting problem is solved. But still, the data generation problem is a problem, right? So what we suggest in this paper is to use data augmentation in order to come up with new weight space data. And the main idea is to use weight space mix-up. As you can realize by now, what we do is we use some alignment algorithm in order to align those two networks, and then use a convex combination of those two. And the results are pretty amazing. We show that here, the blue line shows the loss without augmentation, and there is a severe overfitting. When using the augmentation, we see that the problem is more or less solved. And the same thing can be seen here, where we show the test accuracy, and you can see an improvement of about 10 points here when using the augmentation. So I believe augmentation for weight spaces is extremely interesting, both I would say theoretically, to understand how to create weights for that are meaningful from different sets of weights, and also practically it's going to play a significant role in weight space models. Okay, so let me conclude. First, I guess I don't need to tell you because you came to this workshop, but equivariance is a very effective way and very effective design principle for neural networks for structured data types. I would add that the math is also very fun, at least I like it a lot. And for weight spaces, weight vectors are becoming an important data modality. And what we saw in these works is that equivariance is key to success in this case. There are multiple works. This is really starting to gain the attention of the community. And I think there are lots of new exciting directions, both on theory and applications of that. And if you're interested, then yeah, I'm happy to talk about it. And yeah, that's it. Those are the papers that I discussed today.
Thank you so much, Hagai, for the super exciting talk. So probably we have a couple minutes to take a few questions from the audience if anyone has questions. Okay, Kostas, yes.
Are you gonna keep repeating the questions or?
Guy, can you hear Kostas talking right now?
I
you
heard
can.
Kostas.
So, Haggai, this is really great talk and great direction for research. I'm wondering whether you have made any thoughts about applying this not to weight spaces, but other functional representations, like obviously like 3D Gaussians or any other like basis to describe like a function.
Yeah, interesting. I think this is a natural extension of what we did here. Obviously, we need to think about the symmetries of those representations and then understand how to work on them. But I think it's very exciting.
Yeah, thank you so much, Haggai. Actually, I also have a question. So, as you mentioned in the talk, so like you're focusing on the symmetry of the weight spaces of the neural networks, which are super cool. So I was wondering, like, because the neural networks, they themselves as functions, they're also representing certain entities or certain objects in the primal space. So, and also like for the primal space objects, you also have symmetries there. So probably one analogy is that for point clouds, you have the permutation symmetry for the points themselves. And then for the objects represented by the point cloud, for example, a chair or a car, you also have like rotation or translation symmetries, which like further like on top of the point cloud networks, you can further incorporate like other symmetries. So I was wondering like for like weight space neural networks, is it also possible to further incorporate the symmetries of the objects represented by them? For example, you have an implicit representation for the MNIST digits. You have the symmetry for the weight space of the representation, but you can also have like translation symmetry for the digits images themselves. Like, would you also consider certain extensions?
Yeah, this is a great question. I don't have a concrete answer to that. I think something in this direction can be done. We are thinking about it now, but I'm not sure if I have a good answer now. It can definitely be interesting to be able to encode those object symmetries in the INR itself as well.
Yeah, thanks for your discussion. And in the end, this is really an exciting talk, and thank you so much for presenting your cool works here.
Thank you again for inviting me. It was really a pleasure.
Cool, thank you.
just going to the right. I see it's going to be a little bit different from even. I don't know what's going on now with why this has disappeared. It's a bit problematic. Let me try something. Well, that's not ideal. Well,
You probably can make the window bigger.
then this will cover the screen now. Okay, I can. So maybe it's okay now. Except I cannot advance the slides now. If I click,
I think there's a button here. Yeah. Sorry.
okay, sorry for the technical difficulties. Let me start by thanking Kostas and Congue and Jahui and all the organizers of this nice workshop for the invitation. Equivariance is a truly exciting topic that cuts across many different fields, not just in computer vision, but in many other areas in computer graphics, in robotics, in physics. I'll talk about enforcing equivariance in two somewhat different settings. The first is the more classical one, where we have a known action group, like the rotations or the permutations, and then we're going to have neural networks that support that. The second is one where the symmetries or the maybe I have to speak closer to the mic. Is this better? Okay, sorry. So I was saying I'm going to speak about equivariance being enforced in two different settings. The first being one where we know in advance the particular action group we would like to support, maybe rotations, maybe permutations, like Hagai was mentioning. The other is where the equivariant entity is learned from data, perhaps with the help of foundation models. And then by enforcing it, we have tools that allow us to manipulate our data in ways that reflect and support its structure. My setup is not exactly what I expected, so I may have some difficulty here. But let me start with the classical setting of enforcing classic invariance and equivariance for 3D objects. I guess ever since Descartes invented analytic geometry, we have the issue that when we represent geometric entities algebraically, we are giving them in a particular coordinate system. And of course, the coordinate system is sort of a nuisance factor most of the time, because if we have a different coordinate system, we get a different representation of the geometry, yet the underlying real geometry has not changed. So we would like to be able to guarantee invariance or equivariance to these kinds of changes. And so how to handle this kind of geometric transformations has been a classical topic of interest for a long time. Now, when it comes to machine learning, in the early days of 3D, we found it was a lot easier to do standard type of discriminative learning, like classification and segmentation, if we align the shapes that we apply this to, because then the network has an easier time since the information is given in more compatible ways. So in the early days of the ShapeNet, we spent considerable effort trying to align objects that belong to the same class, so that all the chairs are aligned the same way, or the cars are aligned the same way, and so on. And that led to quite good results in things like classification and segmentation. But if you are given an object in a different pose, then this network may fail. So what we would like to do is to support natural invariances and equivariances. For example, the class of an object should not depend on the pose. You know, if the aeroplane is posed this way or that way, it's an aeroplane. We would like segmentation of an object to be equivariant. If we rotate the object, the segmentation should rotate with it. And then there can be mixed situations. For example, for reconstruction, we may want to have an equivariant encoder followed by invariant decoder. Formally, and I guess Hagai has covered this also, the notion of equivariance is we have an operator that acts on the data, and we would like to have in the computed output, have another operator that's a function only of the original operator that represents the output. And the two classical cases is if the action of the operator is the same on the input and the output, this is the equivariant case, or when the operator on the output is the identity, we have the invariant case. How to make that happen is, of course, a topic of many works and of this workshop. The most trivial way, so of course we want all that because that's how we think about the world. We don't always think of the coordinates, we think of the object, sort of in this canonical frame. And if we have this ability to take objects in any pose, then we can be more general. And the real world, of course, that's how the information is given to us in arbitrary poses. And we avoid the costs of doing the obvious solutions, of which the most obvious one is good data augmentation, namely to take the original data and then generate variations by rotating the object and then training the network with a large data set. But of course, this can be quite expensive, and it's also not perfect because, of course, this is an approximate equivariance or invariance. It's not really built into the network. This is the setting of the first enforcement I will talk about. In the second one, I'll talk about learning and leveraging certain covariation patterns in 3D scenes. And these days, we are seeing quite a lot of efforts on nerves or Gaussian splats that give us representations of 3D scenes that can be computed from posed images very efficiently and give us very good results for a new view generation. But at the same time, these are really low-level representations. They don't really understand the scene structure. They don't give us any way to edit the scene in semantically meaningful ways. And one way to approach this is to try to think about the relation between scene structure and scene variations. So let's imagine we have this indoor scene, and let's try to imagine not only what the scene is, but how it could be different. Well, you can imagine that maybe this table here, maybe this chair here, can move a little bit. Or maybe this table can become a little bit longer. Or this table can become a little bit darker. This is a natural semantic variation space of the scene. And what this means in terms of the visual elements of the scene, whether you think in 2D pixels or 3D points, is that there are certain natural dependencies or covariations. That is, these pixels that belong to this chair, A and B, are much more likely to change together than, say, A and Z. Similarly, X and Y are much more likely to change color, change position together than, say, X and C. And this is another kind of equivariance, certain things that vary together. Understanding that is really a way for us to understand the structure of the scene, to parameterize essentially the tangent space of the scene variations using some lower dimensional parameterization that reflects our understanding of the scene. One way to approach this is by bringing in foundation models, because they understand the world, and perhaps for semantics, the most classic one now is Dino. Dino gives us colorings, features that reflect semantic similarity, semantic consistency. And there have been many works trying to extend this 2D semantic information to 3D by essentially distilling it from multiple views, like in a nerve, to the MLP by adding one more head to the MLP that now computes semantics. So now you have essentially another channel that you can use to structure your data. There's also an interesting connection between, or difference between, first order supervision and second order, because normally when we train these neural representations, we ask that they match attributes of a particular pixel. We say this pixel should be red or this pixel should be car. But it's also interesting to think of supervising with second order information. We don't say what something is, we say what something should be the same as. We supervise with relationships. And this is a bit more like the difference between semantic segmentation and instance segmentation. And this second order information is, again, this covariation pattern that I'm talking about. Certain things will change together. And so now we have foundation models like some that give us nice instance segmentation. They give us kind of groupings that, again, we can try to lift into 3D and get some information about what parts of the scene are somehow the same and therefore will change together, either change color or change position and so on. And that's the second kind of equivariance I will try to cover. So again, this is a summary of the talk. The first will be about the traditional prior equivariances, and the second will be about these learned equivariances. And let me start with the first one. Of course, this is a classic topic. I will not try to survey all that has been done. There's a lot, and there'll be many more discussion of this later on today. I'll just present one work, the vector neurons, which is a very low level way to realize equivariance. And incidentally, that was the first research project of Hongyu in my group when she started. As compared to other methods, vector neurons have the attractive feature that they are very simple. They don't have complex math in them. There's no Wigner matrices, no spherical harmonics and so on. And because they are so basic, they can be applied in many different architectures. And the idea is extremely simple. Our normal neural nets, the basic neural net that we all know and love, operate on scalars. Well, let's extend them to operate on vectors. In this case, I will discuss the case of 3 vectors, but it could be any dimension. So it's not just vector input, it's vectors all the way. At every stage, all the intermediate layers are sequences not of scalars, but of vectors, and the output is also vectors. And this is, of course, attractive from the point of view of, say, learning 3D equivariance, because now operators like rotations can be applied at all layers of the network. And that's the basic idea. Equivariance should be kind of rotating the input, and then running the network is the same as running the network and then rotating the output. And that makes sense now because our latent space is not just a vector of scalars, it's a vector of 3 vectors, and those 3 vectors can be rotated by the same operator. Yeah, so this is really just this very simple idea, going from scalar networks to vector networks. And so classically, if we had a 3D shape given as a point cloud where we have endpoints with 6 channels of fixtures, each of them of dimension 1, now we will have the same thing, only each channel will have 3 coordinates. It's kind of interesting that, say, for the point cloud case, we map an unordered point cloud in real 3D to an ordered point cloud of fixtures in this latent 3D. Okay, to implement this scheme, we have to realize all the operations that go into a neuron. The nicest and simplest one is a linear layer, and, say, multiplying the weights of the network by a matrix can be extended to multiplying this, n by 3 matrix by some other matrix, W on the left. And the nice thing now is, because of associativity of matrix multiplication, if we post-multiply the input data by a rotational matrix on the right, because of associativity, that will be naturally the same as first multiplying by the weight operator and then post multiplying by R. So you can kind of, you first multiply by R and then by W, or first multiply by W and then by R, and you will get the same result because of associativity. And so this is this linear layer setting. This is very straightforward. And notice we don't have a bias term here to make this work. The interesting layer is in a linear layer, where, for example, in a standard neuron, we may have, say, ReLU, nonlinearity. That's clearly not equivariant. So we can try to lift this ReLU from 1D to 3D. Essentially, instead of using, say, the X direction, we will learn a direction and then define essentially the clipping that the ReLU does with respect to this learned direction. So if our new vector is going to be kind of projected into the positive half space defined by the secondary direction that we compute. And that is shown in this diagram here. And mathematically, it corresponds essentially, if we point in the positive half space, nothing changes. If we point in the if we have a component in the negative half space, that gets clipped. And by the way, this also works not just for rotations, but also for uniform scaling, something that I will use later on. So this is essentially how we can deal with a certain type of nonlinearity by using this high-dimensional ReLU, and one can do similar things for other types of nonlinearities. And this idea of learned directions can be very useful in other settings also. For example, let's think about the pooling. Well, average pooling, of course, is linear, and there's no problem with it. But if we were to do max pooling, again, you max, now you don't have scalars, you have vectors. So again, you learn certain directions, and you max pool along these directions. So the new thing that the vector neuron brings is these learned directions on which you project your 3D vectors to do the classical ReLUs and pooling. Right, and I just mentioned this, so we'll skip it. There's also, of course, various kinds of normalizations that have to be fitted into this vector form, and layer norm and instance norm and dropout naturally fit. The one that's a bit problematic is batch norm, because there you are mixing different data that may come in different poses, and it's not quite okay to to average those. So for batch norm, we apply the batch normalization process not to the vectors themselves, but to their norms, because these are invariant. So basically, these are the building components that go into equivariance. And for invariance, it's a very small variation. Namely, we simply use the fact that if we start from some input and then compute two equivariant outputs and multiply one by the transpose of the other, we will get something that's invariant, because, oops, I don't know why. Yeah, because if we apply a rotation matrix to the first one, we'll apply the transpose rotation matrix to the other one, and because R is a rotation, R times R transpose is identity, so we get the same result. We get invariance. And in particular, in our setting, what we do is we use identity as the first vector neuron, and then a second vector neuron that essentially computes a coordinate system, a 3x3 matrix, in which the result will be expressed. And the product of the original times the transposed coordinates gives us something which is invariant, sort of a canonicalized set of figures. And we found in practice it helps to do this not on a per point basis only, but also append the mean from all the points, because somehow this gives the network information about the entire shape and not just this one point. So this is how you can build an invariant layer into this network. So that's really a summary of the vector neuron. That's all there is. And now we can take, sort of classical 3D networks and vectorize them in this form. For example, we can take dynamic graph CNN, which essentially is a graph neural network operating on a point cloud in 3D. At every step, we do an X convolution to our nearest neighbors, learn some new feature, recompute on the nearest neighbors using this new feature, and then do it again. So the basic architecture is this sequence of XConvs and nearest neighbor computations, which what it does basically is to transition as you go through the layers from a notion of distance that is more geometric to a notion of distance that is more semantic. And in terms of transforming this from a standard neuron to a vector neuron, it's really extremely simple. We simply just replace all the components by their vector neuron counterparts, and basically that's it. And we can do the same thing for another classic network that was mentioned by Hagai, also PointNet, where essentially we lift the points of a point cloud into a high-dimensional space by a learned mapping, and then we average them or max put them to compute a fixture. Here too, we can just essentially vectorize the operations. There's a little bit of a tricky part in the first layer that I will not have time to mention. And so we can get essentially a vector neuron version of the PointNet. And so we played around using these vector neuron networks for many classical problems like classification and segmentation. And I show here a number of different setups. I have a slash. To the left of the slash is what we train on. To the right of the slash is what we test on. Z means kind of vertically aligned shapes. This is the classical. SO3 means arbitrary poses. So here is test, train on vertically aligned, test on vertically aligned. Train on vertically aligned, test on arbitrary. Train on arbitrary, test on arbitrary. And the results are shown here. The first 4 rows show the standard PointNet and DGCNN and their vector neuron counterparts. Below that, there's a group that does not try to optimize for rotations. This is for a fixed pose. And the second last group are methods that try to optimize for all poses. And you can see that the vectorized networks here do the best. And it's interesting because they do better even than the versions of the same networks trained with augmentation. So it says that somehow building the equivariance directly into the network is better than trying to do data augmentation. And here you can see something very similar happening for segmentation. And we also played a little bit with reconstruction, where you can see like a classic network like occupancy networks has a real hard time trying to reconstruct shapes when it's trained with shapes aligned and given something that's in a different pose, unaligned in many ways. Okay, short on time, so let me move quickly to the, I have some applications of vector neurons, and because I'm short on time, I just mentioned them very quickly. So one is...
We introduce equivariant neural field expectation.
I'm sorry.
However, two main challenges arise when we try to generalize the knowledge of single object shapes to the scene.
I had to cut this off, but it came on. Right. In this work, the idea was to train the network in an equivariant way on shape-and objects, but then be able to detect these objects in scenes where there's multiple objects in the scene, all close to each other, but without any supervision at the scene level. All the supervision is at the object level. And as you can see here, the basic building block is a Vienna encoder that takes a point cloud, encodes it into a representation that then is decoded into an SDF. And you can see that because of the Vienna encoder, as you scale and translate and rotate the point cloud, the output also scales and translates accordingly. And then to solve the scene problem, again, I don't have time to go into any detail, but the idea is you simply take your scene and take chunks of the point cloud and try to reconstruct them using this network that knows about shape-net objects. And this gives you some reconstruction. and then you reassign points to the nearest object and iterate. It's a classic EM type of approach. And you can see that it can handle quite a complex scenes that involve multiple objects in close proximity. And it's a new data set that we created that have chairs and mugs. The second application that I very quickly mentioned is one where we try to learn equivariant visual motor policies for manipulating articulated or flexible objects. And so again, the setting here is that we will generalize from a demonstration that involves some object of a particular size to an object of a very different size. And since I'm short on time, I will skip all the details and then go straight to some videos. This is some demonstrations of close folding, object covering, and box closing in simulation. But we actually have tests of this in a real lab setting where we have two ceiling cameras that observe and give us images and point clouds, and then these two mobile robots with over arms. And here you can see what they were up here is what they were trained on, or the demonstration, and down here is the target. And you can see some of the demonstrations here. And then the application to objects doing the same type of motion, but in a very different size context. So these are applications of vector neurons because the features that are used here are computed using a vector neuron encoder, a Siamese vector neuron encoder. Okay, I have 15 minutes, so I'll go very quickly over the second part where we have learned equivariance. And, if we build a nerve model of a scene, we have some knobs for varying the scene. These are the parameters of the MLP that defines the network. But varying the parameters of the MLP will not naturally vary the scene in ways that are sensible. For example, if you randomly vary the MLP parameters, colors will change and so on, but you will not see something that is meaningful. So the goal here was to try to, it's a bit like Hagai's approach of working on the weight space, to work on the weights of the network so that in this new weight space, then varying the weights produces meaningful changes to the scene. And this is a little bit like a classic hypothesis from neuroscience that neurons that wire together, this is the so-called Hebbian hypothesis. So we would like essentially to build resonances between things in the scene that should change together. And in the MLP case, what we can do is this. So we can take our nerve and take, say, 2 pixels, one in this view and one in that view. And if we think of the network parameters as being random variables, if we add some noise to them, then one can talk about the mutual information between those 2 pixels, right? And it turns out that this mutual information is really captured by the alignment of the gradients of these 2 pixels with respect to the network parameters. So what we would like to do here is to use information about what things covary to align the gradients of the pixels that give rise to things that should covary. So effectively, we are trying to project the network into a lower dimensional space where these equivariances are enforced. And that's shown a little bit here. Here we take this scene, we have a whole bunch of points. Some belong to the same class and some not, shown here by color. And we would like, after the shaping, to guarantee that the gradients of these pixels with respect to the network parameter align for the pixels that belong to the same class. And we do this via contrastive learning, of course. And in this small MLP setting, what's going on is that we just train the last color layer of the MLP according to this to this contrastive learning. And it's a very, very lightweight training. I mean, we just have 64 batches of 64 raised pixels across all views. And that somehow suffices, because somehow contrastive learning is like transitivity of equality. If A resonates with B and B resonates with C, then A will resonate with C. One can also do this in 3D, because in this network, it's possible to compute depth and push the information back to 3D. But I don't have time to cover this. But what it gives us is, say, if we have, say, this original view from a nerve, and if we, say, vary the gradient of this pixel, in the unshaped nerve, everything changes. But once we have shaped the nerve, only the resonating pixels change. Essentially, we have learned how to select semantic entities in the nerve. And this shows this example, again, where in this so-called Jacobi nerve, because we deal with Jacobians, we are able to essentially learn the semantic components out of this contrastive learning. And this works even if we very slightly perturb a pixel. Again, we can see the ones that change are the ones that belong to the same class. And so now that we have this, we can do information propagation in a very lightweight way. Namely, we can take one view, annotate just a few points with a semantic class, and then propagate this not only to all the pixels of this view, but to all the pixels of all the views, because we can see who resonates with the ones we selected. And so this is an example where we annotate just the shown pixels here in this view of this replica scene, and then somehow we have annotated the whole nerve, all the views of the scene. And this is an example with SkyNet. One can do better if you annotate all the pixels in one view. And because I'm short on time, I will not dwell on that. And here you can see some numbers. For example, even by annotating a single pixel per class in one view, you assign correctly about 50% of all the pixels, which is not bad. And if you do all the pixels in one view, you get up to 85%. And even more, what you can do is start modifying this scene. For example, I can take this ceiling and change the color of one pixel, and the whole ceiling will change color, because now my network has learned that the ceiling points are equivariant, they change together. Notice that this preserves the lighter part near the windows and so on. So this example shows that we have essentially a way to manipulate the scene. Our nerve has learned some structure that allows us to manipulate the scene in structured ways. And the very last thing I want to talk about is doing something similar, but now in a Gaussian splatting setting, but for motion. Again, we all know that Gaussian splatting gives us very nice reconstructions of static scenes. And there's been work also to extend this to dynamic Gaussians. Many of them work by essentially taking a Gaussian and having a small MLP that predicts changes to the parameters of the Gaussian's position and pose. A change in the x-coord, in the x position of the center, the quaternion defining at the rotation, the scale, and so on. And now we can use some supervision to tell us that perhaps certain Gaussians belong to the same object. Again, some is our learned equivariance. And so now what we can do is in this motion MLP, we can do contrastive learning so that Gaussians that somehow belong to the same object, that resonate, move together. And we can do this without having any motion. We can take a static scene and do this. So we can essentially, using the sum masks, take pixels that fall in the same mask, see which Gaussians they come from, and do this gradient alignment that I talked about between the Gaussians that should align versus, say, Gaussians that give rise to pixels in different objects that shouldn't align, should be orthogonal. And again, so you're doing the shaping in the white space like before. And I will not discuss the mathematics behind it. I don't have time. Let me just show you some results. This is a scene from Mipsler E360. This is a static scene, just the camera moves. If we look at these Gaussians, and if we take a particular Gaussian on the tractor, say the small Gaussian shown here, and try to see which other Gaussians in this whole scene it resonates with, we see that after we've done the shaping, it has picked out the tractor. And notice, we have not looked even at all the Gaussians. Essentially, there's about 8,000 Gaussians in the bulldozer, but in the contrastive learning, only about 460 of them were touched. So somehow, the structure of the MLP, the structure of the moving agent, gives us the extension of the supervision to all the Gaussians. And having done that, now you can see the tractor is moving and nothing else moves. And here's another view of the same motion to show you this is really happening in 3D. It is not 2D. And let me end with a few more examples of this. Here's another scene from Lurf. And again, this is a static scene. The camera is moving. I'm going to move the pumpkin. Here is a pumpkin. Here is a Gaussian on the pumpkin. And I show in color the Gaussian that resonate with this white Gaussian. And it kind of selects the pumpkin. So now we can move the pumpkin in the scene, even though the scene was originally static. And again, we supervised very few of the Gaussians. And again, we have learned essentially this equivariance of this group of Gaussians through this contrastive learning. Here's another view of the same motion. Again, this is happening in 3D. It's not 2D. And as a last, here's some more examples of this resonance kind of visualization. And you can see it is not perfect. I mean, there is leakage here that you can see. This is this chair here, and you can see that it is leaking onto the table. But overall, it is remarkably good. And here's the last scene I'll show. This is again a Lurf scene. Again, it's a static scene. Here the camera moves. And then I'm gonna here move the apple, move the tea bag, and the cookie jar. And as you can see, the apple move, the coffee bag move, and the cookie bag move. And this is the same motion from a different angle. Again, this is fully 3D. Okay, so I can finish on time. Let me summarize what I talked about. Equivariances can be known to us in advance, and we want to enforce them. And the vector neurons was a way to try to do that by essentially using these building blocks at a very low level of linear layer, nonlinearity, max pooling normalizations, and invariance. And then we saw how, for example, this can be used in the case of the GCNN and PointNet to give us very good results. And in the case of learned equivariance, I try to show how we can build these resonances between the building blocks, the low-level building blocks of the scene that can be learned using foundation models that sort of tend to understand the scene structure. And then once we have built this kind of resonances, essentially we have bonded the molecules that form the scene, whether it's the Nerf dust or the Gaussians. So now the scene has a structure, so that if we try to change something, other things that covary or equivary with it also will change. And I think that's the end. And thank you, and I'm happy to take questions.
Thank you.
Thank you so much for the super exciting talk. So we can take a few questions from the audience, although we don't have much time.
Can you hear me?
Basic question, but what is symmetry and is it a group?
Sorry?
What is symmetry and is it a group?
Symmetry. What is symmetry?
Symmetry, the similarity group. Symmetry is is rigid motions and uniform scalings, similarities, symmetry. Yeah, sorry. Yes.
Can you hear me?
From the great talk, I have a high-level question. So we talk about building equivariance with hard guarantees, like we know the groups, like isometries. We also talk about how we learn that from data.
Right.
The question is, do you have any sense of, is there anything between them that we can apply some kind of known structures, but also make it arise from the data? Like, for example, we can have some kind of constructed way to build a network that obeys some complicated rules that hide in the data.
Absolutely. I think it's a very exciting area. I think in some sense, I presented two extremes, right? The one where you know everything in advance, and the other where you learn something really local. And the examples I was showing is kind of learning Gaussian, say, groupings that give rise to rigid motions. But since you have articulation, now the motion of my elbow, I mean, of my lower arm and the upper arm, I mean, they're different parts, but their motions are coupled because of the joint. And how can we learn, and we know in advance, certain kinds of dependencies that arise in the real world? So I think it's very exciting to be able to couple priors coming from the foundation models and priors coming from the dependencies of motions that we know exist in the real world. Yes.
Chance that will break the equivariance because you're applying on two different scenarios and real world scenarios are always challenging.
Thank you. Yeah, that's a very good question. The question was, what happens if the equivariant breaks, especially in these learned settings, because nothing is for sure. And I mean, actually, I think Jahu and I had this discussion just last night, how to do something where essentially there's a symmetry or equivariance that holds almost all the time, but you want to also allow it to break sometimes. And I don't really have a good approach for this right now, but it's a very nice, I think, to work on. More questions? Yes.
Of the natural things, like it is confined by the gravity, so if a chair is there, we usually assume it's rotating like through the z-axis, but not all the way around. Do you have any in mind, like how to apply it in real applications with with some limited requirements, but not the really strong SOP?
Yeah, I have to think about that. I mean, in the network shaping I was showing, I talked about you projecting the parameters of the network to a lower dimensional space that enforces the equivariance. But maybe it's not really fully projecting, but bringing things near a lower dimensional space. So you still allow some deviation. But how to properly handle that, I don't know right now. I think it's a very nice question to address. Yes.
Abstract question. Can you comment on the relationship between equivariance and disentangling? And also, in disentangling, you kind of think of it in terms of independence assumptions, or you can think of it as statistical independence versus functional independence. I think of equivariance more in the functional sense, but I don't know. I would love to know your thoughts.
Yeah, it's a very good question also. And when we were doing the vector neurons work, we found that when it came to testing on aligned shapes, we were doing a little bit worse than the network that is trained on aligned shapes. And we never fully understood why that was, but my hunch was that it's because there's some fundamental ambiguity between shape and pose. That is, here is my hand. If I twist my hand very slightly, is that maybe a different shape in this pose or this shape in that pose? And so there are these situations of imperfect disentanglement that I think somehow we have to allow. So, these perfect factorizations are nice mathematically, but in real life, they don't always work. And how to handle them is, again, in the spirit of the several questions we had, it seems there's some consensus that this is something important to address for the community. Okay, thank you.
Thank you. Yeah. Okay, cool. So, welcome everyone back to the second half of our morning session. So now we're gonna have our third invited speaker for the day, Eric Beckers. Unfortunately, Eric is not able to travel here in person, but he will deliver this super exciting talk virtually on Zoom. And let's welcome Eric. Eric, can you hear us? I think you are muted.
Okay, yeah, I'm in. I can hear you.
Oh,
Can you hear me too?
sorry, we cannot hear you. Let me. Sorry, can you speak it again?
Yeah, can you hear me?
Oh, cool. Yeah, we can hear you now.
Okay,
Sorry,
that's
it was
great.
my setting. Yeah, thank you so much.
All right, so first of all, thanks a lot for inviting me here. Be it virtually, I'm still
Oh,
very.
actually, sorry, I forgot to introduce you.
But it's fine.
Sorry.
Yeah.
Yeah, let me read the introduction first. So I'm so sorry. Okay. So Eric Beckers is an assistant professor in geometric deep learning in the machine learning lab of University of Amsterdam. And in his PhD thesis back in the days, he developed a medical image analysis algorithm based on sub-Riemannian geometry in the Lie group SE3 using the same mathematical principles that underlie mathematical models of human visual perception. And such mathematics find its application in machine learning, where through symmetries and geometric structure, robust and efficient representation learning methods are obtained. And his current work is on generalizations of group convolutional neural networks, improvements of their computational and representation efficiency through sparse graphs and adaptive learning mechanisms. And now let's welcome Eric for his super exciting talk.
All right. Yeah, thank you very much. And I mean, it's a pity I can be there in person, but I'm still very honored, nevertheless, to be part of this amazing program. I mean, the organizing committee has like an amazing track record themselves when it comes to equivariant deep learning. It's just amazing to be part of a workshop purely focused on equivariant. So it's exciting, and thanks for having me. Yeah, so let me just start with my talk. So it's going to be about a concept which I'm trying to pitch today, like neural ideograms, and the idea of geometry-grounded representation learning. And this geometry-grounded representation learning, that's a concept which we're hosting a workshop on at ICML in a couple of weeks. And this idea of neural ideogram is basically the vision that what I want, and I think many among us want, is to have reliable representations of real world concepts. And when we talk about the real world is geometrical, it's physical in nature, at least it behaves first, through certain geometric mathematical laws. And we want that sort of theory and those tools to be applicable to learned representation. So this is what I'm aiming for. If we have an image, we want to convert it to a representation, a symbolic representation, like a pictogram or an ideogram, if you will, which allows us to reason about their parts, much like capsules or what's happening in point clouds or molecules. And this is something, an idea which we've been pursuing now for a while. And it started off with this idea of a shape space, VAE, so a variational autoencoder that maps to a latent space which captures geometry or shape. So I want to start with that and then move towards more recent work in this line of thought about equivariant neural fields. So this is very recent work, and we just put it on arXiv as a preprint. And basically it allows us to relate visual representations to fields or images, if you will. And in conjunction to it, we applied this to a really nice application where we do forecasting of PDE, so evolving fields, dynamic systems applied to fields, but we do this in latent space, so in this symbolic geometric space. And lately central to all of these methods are some results obtained in our recent iClear paper. And this paper presents a general purpose equivariant architecture for point clouds in 2D, 3D, or homogeneous spaces of the group in general. So I hope I can cover all of them, but it might be that I'm a bit quick on that particular paper. So this figure illustrates conceptually what I'm aiming for. So this is beautiful illustration by Picasso, making an abstract representation of a bool. And it started with a lot of detail, and we have several versions of abstractions up to this point, which is really a bunch of lines. But it's the relative configuration, and this basically it's compressed to a bunch of lines that still capture the essence of the thing, the shape itself. And this I find super intriguing. And this is a concept which we see throughout our society, right? If we work with pictograms, with ideograms, throughout society as an efficient way of conveying information. And here, just to get some terminology straight, when I talk about a pictogram, I mean an almost literal shape representation of the concept that you're looking at, right? This is clearly outlining the shape of a bird. But such a geometric representation does not have to be literal. It can also be more abstract. For example, representing the abstract concept of happiness, of being happy, right? And what I find intriguing that these are geometric symbols, but they do not necessarily represent something geometrical. And well, to me at least, I think many concepts are very applicable to geometric reason, even if it's not concretely geometric. Now let's think about some other types of representations that we encounter in our daily lives. This is a very much compressed representation of the concept bird. It's just a bird, but it's not really applicable to computing, which we as deep learners are aiming for, right? So this is then another class of representations. It could still represent a lot of things with all these numbers, but it's less interpretable, and it's not explicit at all about how geometric information is sort of hidden in these numbers. So what I would aim for, like this is super practical when computing in neural networks. This less so. Well, we could tokenize it, but still you lose a lot of information. And this would be ideal, right? If you're able to reason about geometric relations, the head above the body, etc. So that's what we're aiming for. And just to illustrate the concept, this is just one of many, well, the typical representation learning method, a variational autoencoder, to illustrate the idea that even if we're able to compress an image to a vector and decode from it, we could say, okay, well, this vector contains all information there is in this image, but it doesn't mean that this vector actually carries semantic information. It's semantically meaningful, right? And that's something what we want. So we want actually something like this, where we are able to compress an image to a geometric symbol from which we could still decode the data, because then at least some geometric information is preserved, and we could start to reason about the relative positioning of geometric features. Okay, so naively, this is what we could do, right? We have an image, we can encode it to a point cloud. So we just built a neural network that spits out a bunch of coordinates. But obviously, this is not necessarily leading to meaningful representations, right? Because if I were to rotate the image, the neural network essentially receives a different input, and therefore will predict a different output. And there's no reason to believe that it will predict rotated coordinates, right? It just, these coordinates that the neural network predicts is just a bunch of numbers. Now, of course, this is unless, and now I'm preaching to the choir, unless we make this equivariant, right? So with equivariant architectures, we know that we can design the networks in such a way that if the input rotates, the output rotates accordingly. We can actually spit out quantities, vectors that, transform in a meaningful way. Now, I would argue that these equivariant architectures, they lead to what you could call grounded representations. And more importantly, in the context of shape, like I think in many ways, a concept, like a bird, is characterized by its shape, right? It's really like what it looks like. And shape is, well, invariant to rotor translations, or essentially distance and orientation preserving transformations. Okay, so that's one part why equivariance is important. We want to preserve the essence of the data. But this grounding, actually, with that I mean like both this image is a field or a function over an Euclidean domain, and the obtained representation is a collection of points in the same domain. Okay, so in that sense, I already share some commonality, but most importantly, both can be subjectable to group actions. The same transformation laws that I could apply to the image, I could also apply to the data points. This is really just the principle of equivariance, but I would like to make a slight conceptual change here in that I like to think of these type of representation as being grounded in the same input space or the space over which these functions live. And with grounded, I really mean that these representations are geometrically meaningful. That really points, I can really talk about relational structures between objects and parts. So a short conclusion up until this point. What we get with equivariant architectures is that the representations are physics and geometry grounded, meaning, well, we can talk about transformation laws and relational structures in this representation space. These are some results I'm not going to cover in this talk, but there's plenty of papers in the equivariant deep learning literature that indeed show that these equivariant methods, they are parameter efficient and expressive, well, because of a weight sharing principle. And they actually provide geometric guarantees such as equivariance and invariance. So that's basically by construction. Okay, I just want to quickly drop this paper because relatively recent work by Artem Moskalev was about investigating to what extent data augmentation can be used to obtain equivariance. And the conclusion was simple. Data augmentations do not make a network equivariant. It may seem equivariant, but it is not, and it will not generalize to out of distribution data or this equivariance property. And it's a point which I'm trying to tell for many years now. If you really want equivariance guarantees, there's no way around and using a form of weight tying in your neural network or weight sharing. Okay, conclusion to this point, equivariant deep learning leads to grounded representations. Now I want to give like our first work on actually learning these type of geometric symbolic representations. And this was work done by Chaudhry Vatkama about Kendall shape space variational autoencoders. Just want to give a quick breakdown of what we did there. So we know that with equivariant architectures, we can predict all sorts of quantities like vectors, rotation matrices, tensors that transform via group actions. And so we use this property to have a neural network that predicts a bunch of points or vectors. We plotted them here as coordinates and a pose like a rotation matrix. And since it's equivariant, we know that if the input rotates, both the pose or the rotation matrix and the shape rotates. And we use this property to canonicalize the representation, meaning that if we apply the inverse rotation matrix to the predicted latent, we get like a stable view of the thing. Because if the input were to rotate, this pose rotates, the shape rotates, and sort of here in between, they cancel out. And then you get like a stable representative of the orbit of representations, if you will. So, right, so the essential shape is invariant, but an important remark has to be made here, like this object still consists of objects like points that are configured relative to each other. So invariant doesn't mean that we just get rid of all geometric information. It really means information is preserved. It's just the pose is, the object is canonicalized. Just a brief mention of the VAE framework. A Kendall shape space is essentially a shape consisting of a bunch of landmarks. Maybe let's just go over here, like a bunch of landmarks. And since we want a shape to be translation invariant, well, we could say we could always subtract the mean of it. That removes 1 degree of freedom. Since we use this canonicalization, this shape representation is also invariant to rotations, as a shape should be. And in order to make it invariant to scale, we divide by the norm of the vector. And that essentially maps it to the hypersphere. So if we then use a VAE, it should be hyperspherical VAE. And we know hyperspherical representations have some nice properties. And so that was an additional bonus of this framework, that it's both equivariant and it effectively maps representations to the hypersphere. Okay, maybe I'll leave this as a brief remark, like in follow-up work. We propose a generalization of the classical Kendall shape space framework as stating it as not just a sequence of landmarks or coordinates, but as a sequence of objects that can transform via group actions of the SO, of the rotation group, special orthogonal group. And that means that now we could also predict a spherical signal, which is rotatable, or a sequence of spherical signals, etc. I know it's a bit suggestive, this plot, it's not exactly like this, but it does generalize to a lot of interesting cases. Some quick results. So we applied this. This is an unsupervised framework, right? So no supervision at all. So we tried this on MNIST. And we thought this was an interesting use case because MNIST are really handwritten digits, like symbols themselves. And essentially what's happening, the neural network learns to associate a geometric symbol. So we just plot it as such by drawing lines between them, and it predicts a pose. And interestingly, all these 6s or 9s, I don't know, maybe they're upside down, 6s or 9s, they all receive the same representative shape with some variation, just like we would expect variations in your handwriting. But it still allows for distinguishing 6s or 9s based on the poses. And I find this an intriguing concept because in a way it assigns symbolic representations to the digit 6, just like you would have across the world different types of ways of representing 6. Then, well, let this be sort of the neural network way of thinking about, or thinking. I should not anthropomorphize these concepts. This is what a 6 looks like in the eyes of a neural network. In the same way, such neural networks learn, well, representations for other digits, which are consistent in their shape. And I just find this an intriguing approach. But then we figured out, well, there's one essential drawback from this. And it's like, maybe I should phrase it like this, like there's plenty, or not plenty, there's actually quite some equivariant autoencoder type methods. But we realized that actually none of them are translation equivariant. And this is maybe surprising given that translation is such a simple transformation group. And what I mean with that, if I have such an encoder, I stated before, well, we have a group action on the input space, a group action on the latent space. But in practice, this group action on the latent space is typically the rotation group. And I must mention there are indeed interesting methods that also try to induce translation equivariance, but it's not quite doing the thing in an exact manner. And why is this happening? It's happening because if we want to compress data, we have to do downsampling, right? So a max pooling layer to compress the image to less pixels, fewer pixels until you're left with 1 pixel, let's say. And so these points that you see here are actually direction vectors coming from the origin. And it still represents shape in a nice way, but it's not translation equivariant. So this bothered us a bit. And we didn't clearly see a solution to this until recently. Another limitation, but this is more of the equivariant deep learning field in general, is basically that we want to explicitly apply geometric reasoning. But how do you do this when the geometry is only implicit? And let me illustrate it as follows. Like what I mean with explicit geometry is like point clouds. If I have an atomic point cloud, for example, I can clearly reason about relative distance between atoms, their angles that they make. So because the geometry is really the input. And this is really where equivariant deep learning shines. But if you have image data, the geometry is implicit, right? It's hidden behind the pixels. It's maybe clearer in this type of image, right? It's a 2D projection of something 3D. And just put simple, a neural network only sees a bunch of pixels, but it doesn't see a bunch of coordinates relative to each other, right? So if we want to reason about these things, we need a way of making this geometric structure explicit, move it from behind the pixels to really the foreground. And so that's what we attempted to achieve with equivariant neural fields. So this is recent work by, two Davids in our lab. I think our group has a nice history of producing nice papers by people called David. And So maybe there's a paper coming up with 5 of them, but let's keep that for future work. So this is about grounding continuous representations in geometry, equivariant neural fields. And so before I explain that, I want to explain a bit about neural fields. You heard a great talk by Hagai Maron this morning. So I think you're somewhat primed to understand this. These things are ubiquitous nowadays in deep learning. And the concept is as follows. We consider, for example, images as fields that take as input 2D coordinates and spit out an RGB color vector. And this field is parameterized by a neural network, which is a bunch of neural network weights, theta in this case. Right? So we approximate an image with the neural network and we tune their parameters, theta, such that the field looks like the image. And the nice thing is we can do this for all these images. And in this way, essentially, we construct a database of neural networks represented by their weights. So these things could be considered representations. So in principle, the image of a cat or the concept of a cat is somewhat hidden in this representation. Now, this is a somewhat cumbersome representation to work with in downstream tasks. Though I must admit there's been brilliant work in this direction. You saw a talk this morning, also from our lab in Amsterdam by Miltos, on basically using these neural network parameters as representations in themselves and process them in invariant manner. But basically this idea also sparked new follow-up work, right? And what the next thing was conditional neural fields. And there the idea is if you have an image, you could still represent it with a neural field, but now this neural field is conditional on a latent vector. And what does it mean? It's conditioned in a specific way, typically, like you have your neural network layers, but these layers are now modulated with like a scaling factor and a bias that is dependent on this latent vector. So this latent vector is injected in every layer and that modulates the output of that layer. Now, what does it bring? It brings us that now we can share the same backbone neural network. So the neural network weights are shared over your entire data set. Okay, weight sharing is always good. But maybe more interestingly, now the conditioning factor determine what the image look like. So if I have a pre-trained neural field with its weights, I can change the latents and a different image comes out. And this is convenient because now we have a vector representation associated to each image. And obviously we can just pass this through a neural network to make classifications or predictions. And I think there's this really nice paper by Emilien Dupont and Kim et al. About, well, they call it basically functa, like you have a data set of functions and, well, you should treat them as such. And they use this representation in all sorts of downstream tasks. And that's also what we're going to do. But the difference is that we're not now going to vectorize the image, but we're going to associate a latent point cloud to this image. And this point cloud is going to be grounded in the same geometry over which the field is defined. So let's zoom in a bit. So conceptually, what we achieve is that with each image, we associated a latent point cloud. And this is, again, a bit stylistic idealized, but we'll see some real examples later on. Where we really represent an image with, let's call them just parts, just like in capsules, and their appearance vectors. And we have a bunch of them, they configured relative to each other. And we do this also in the same type of framework. We fit a base architecture, and I'll say in a minute what this looks like, and obtain these point cloud representations for all these images. And we do this in such a way that these neural fields are equivariant, meaning that if I transform my latent point cloud, the decoded image, the decoded field is transformed in the same way. So we have this commutative diagram. And this property is classically known as the steerability property, where we say, well, if we transform a function just as a function, this is a regular representation, the group action acting on the domain, we could also transform the function by just leaving the coordinate grid as is, but transform the representation. In contrast to the classical steerability sense, these do not represent the basis coefficient, but the latent point cloud. And because this is a point cloud, we have a well-defined group representation or group action defined on this representation set simply by transforming the latent poses. These poses, I'm not sure if I was clear about that, but these poses are elements in the group. So this represents, for example, a rotor translation. And we could decide to pick different groups, for example, the translation groups, and then we don't have rotation equivariance. Okay, so a little bit about how did we achieve this? Well, first of all, we want a steerability property because that means that the latents are grounded in the same geometry over which the field is defined. And then we looked at this, and this is a somewhat known result in equivariant literature. Many proofs on equivariant architectures come to similar conclusions when it comes to kernels or one-argument kernels. Basically, if you have the steerability property, that really means this function, which is a function of both the coordinates and the latents. If it's steerable in such a way, that really means it should be invariant with respect to both arguments. And okay, so we need bi-invariance of this function. So that's one criterion. So we realize, okay, that's something that we need to cover. Secondly, we want the representation space to be flexible. So we want it to be a set. And we want the set to carry geometric information, so it almost automatically becomes a point cloud in some geometric space. And so when it comes to set latent representations for fields, we actually took this nice paper as an inspiration, the 3D shape to vecset paper. This uses a latent set, but did not carry any geometric information. So there was no way to make this equivariant. And that's, well, conceptually the simple fix that we apply to this. In addition to figuring out what equivariance means in this context, we basically made the latent point clouds, the latent set, latent point clouds. And so that means if you look at the attention equations, since we want all this entire field to be invariant with respect to transformation on X and Z simultaneously, we should look at every instance where we see an X and a Z or an X and a latent point. And so we have to work with bi-invariant attributes. And this was precisely which we derived in a recent iClear paper on fast expressive equivariant networks. Maybe I'll say a bit about this at the end of this talk. But really that's the essence. So we have a transformer architecture, which we condition on pairwise attributes between coordinates and poses. And these pairwise attributes to be bi-invariant. And that's what we, in this paper, we list all possible invariants. Yeah, and so this is then a summary of the method. So we have an image, we could fit a latent point cloud to it, and this latent point cloud generates the image via a cross-attention method. So it really also means that these latent points, they are responsible for generating a local part of the image. And this has some nice explainability benefits. Same, we applied this also in 3D. For example, to fit shapes with sign distance functions. And we achieve this equivariance property, which follows by making sure that the attributes that we use are invariant with respect to both slots. Okay, so we started fitting images. And first it was a sanity check, like, okay, how well do we represent images? Does it indeed satisfy the translation and rotation equivariance properties? So as said before, like the only thing or the main thing to take care of is making sure that these attributes that you condition your transformations or your transformer on, both the value transformer and the attention, that these attributes are invariant, and then you can choose which group it has to be invariant to. So if you choose it only to be translation invariant, then you see, well, if you rotate the latent point cloud, something really distorted comes out. But if you translate it, it indeed preserves the translation equivariance. And then there's different ways of coming up with invariant attributes. And in the iClear paper, we derived which attributes are actually optimal in a certain sense. So then you see, well, we can steer these fields however we want. So if you look pure at a pixel, a peak signal to noise ratio on Cypher, CLAP-A, and SCL10, this is really a measure of how well are these neural fields capable of representing images in the first place. And over this entire data set with the shared neural network parameters with specific latents fitted to the image, just like in the functor paper, which we took as a baseline, we see that we get excellent, fitting capacity. And recall that for the functor paper, we fitted vectors, and in our work, we fitted these latent point clouds. And I think partially why it works well is because of the general equivariance principle that we have been preaching. Like we have an increased form of weight sharing. Weight sharing is good. And we have actually a notion of locality, so that really we are able to share patterns over local patterns, right? So if we are able to construct a local signal, then we could also do it here and here. And this also improves data efficiency. But the main thing that we wanted to focus on is that these representations are actually meaningful, right? Semantically meaningful. So that's what we can test by passing these things through a neural network. So in this case, it should be like a permutation invariant graph neural network. If you process the weights of a neural network, if you have an MLP or like a vector representation, it could be just an MLP. And in our case, now we can use an equivariant graph neural network that is capable of learning to see patterns in terms of relative configurations. So this is what I'm really excited about. Now we make the whole tool set of equivariant deep learning for point clouds applicable to image data in a certain way. Yeah, so this is then what the results look like. Again, functor as a baseline, which fitted all these vectors. And indeed, it's hard to sort of reason about the content of this vector, right? Still, you get quite reasonable results on Cypher 10. It's not, it's not the best, but if we just out of the box learn or apply a graph neural network on the latent point cloud, we get 82% accuracy. So what it tells us is that with the same fitting paradigm, we actually get quite an increase in representation capacity or semantic meaning, let's say, of these latent representations, because now all of a sudden the geometric information is explicitly present. Yeah, this is just a nice figure. It's about, editing of neural fields, because now we have this locality property. We can start to edit really structures locally. And just to illustrate what we did here, if we have a fitted point cloud using our equivariant neural fields, we can decide to take the points of one image and just swap the two halves, and it stitches it together. And what I find surprising is that it kind of stitches it in a somewhat natural way, right? That the neck is nicely outlined. It's not just that it cuts like a border like this, but through this cross attention, we sort of see like a soft segmentation of parts. And I think this is a nice feature of these equivariant neural fields. Yeah, so maybe the final part is going to be like another application which I'm excited about. And this is the idea of PDE forecasting in latent space. Again, with the same Davids, backed by an amazing team of PhD students and Stratus with a lot of experience on dynamical system modeling. So the idea here is, maybe let me first skip to the next slide. So if you look at PDEs, these are really just fields that evolve over time, right? They're governed by a certain partial differential equation of PDE. So if you have an initial state, we let it evolve, so there's a bit of flow involved, there's diffusion going on. So we see these patterns evolve over time. And this is what we want to model. So we want a neural network. Obviously, there's amazing PDE solvers, but this is just to prove the concept that we could also solve these PDEs in a very efficient manner via neural network surrogates. And the approach that we took here is that if we have an input field, we can encode a latent representation, like this symbolic geometric representation that I've been talking about, via an equivariant encoding. And we use principles of meta-learning and auto-decoding to map an image to its latent representation. Then we learn an equivariant neural ODE, so basically an equivariant function that predicts what the next state should be of this latent point cloud. Let it evolve and then read out the result afterwards. And also this is equivariant because the neural field is equivariant. So we have a fully end-to-end equivariant method to process data in a latent representation. And the results are actually quite impressive. So this is our predictions, and it stays quite close until quite some steps into the future relative to the ground truth. Now, there's obviously very good methods already out in literature that does this. The GFNO is one of them. And what I want to stress here is that we come certainly close to these methods. But maybe most importantly, somehow our method is way more efficient when it comes to data or fitting solutions or learning solutions based on less observations. Because that's the nice thing about neural fields, is that we can arbitrarily sample pixels in the image. It doesn't have to be every pixel. It's just a neural field, so we can do it wherever we want. And so we show with even 5% of the sampled pixels, we barely see a degradation in performance. And I think this is really opening doors for very efficient and scalable methods for, learning dynamics in data. Yeah, and this is just to show that this concept of equivariant neural field is not limited to images. I said the main thing to figure out is what are the attributes on which you're gonna condition the transformer. And basically you could do that for different type of geometries and different type of symmetries that you want to preserve. And here we did this for the shallow water equation on the sphere. Also there we got nice forecasting methods, and it works well also in sort of upsampling super resolution approaches. We did the same for the internally heated convection in the ball. And okay, this is just a visual of indeed equivariance is indeed equal to data efficiency. So we see that we are way more data efficient, that we can quickly reach great performance with less data. Yeah, so I think I maybe have a couple of minutes left. So I just want to give a quick pitch on what we use in all these methods. So I already talked about these invariant attributes, and I talked about this equivariant neural ODE. And what we did here was use a recent equivariant architecture for point clouds. So we presented this at iClear a couple of weeks ago, a month ago. Sharvi and I ran this project backed by our amazing team. So what does that paper offer? It really offers a practical method and code, both PyTorch and JAX, for equivariant graph neural networks. It presents a complete set of pairwise attributes to build any equivariant SEN equivariant neural network. And basically we add a more conceptual, wouldn't say novelty, but a reiteration of the statement that convolution is all you need. Okay, what I'm going to do is just show a bunch of results to, to convince you that the method is really useful. So we applied this for energy prediction of molecular states and their conformations. So we reached really state-of-the-art results, but actually in a way more efficient manner. I'm not sure if you see it, but NeckWeb, and this is with their optimized code, it takes 20 seconds per epoch. In our code, we re-implemented NeckWeb. For us, it took a minute, so they did some clever tricks to speed it up. In our code, it took only 6 seconds per epoch, but still outperforms them. And the nice thing is that almost all these methods are based on tensor products, on Clebsch-Gordon tensor product and the steerability or tensor field principle. And ours is based on invariance alone, just like GemNet, but in a slightly different way. And I want to make the statement that Ponita actually falls in the class of group convolution methods, just like NeckWeb and many other methods. It's just we approach it from the regular group convolution point of view. And the summary here is that our simple method is as expressive as tensor field networks, but it is as simple as EGNN in the sense that we do not use Clebsch-Gordon tensor product and only use scalar values. So that also means we don't have to worry about what kind of activation functions we use. Additionally, we rely on actually also another paper by Guy Meron together with Diem to show that these methods are, or Ponita method is a universal approximator. And another nice perk is that we named it after a Pokemon, a fire Pokemon, which is super fast. And okay. So, okay, we found that applicable. Finally, it also works for generative modeling of point clouds. And here I again want to stress that it's important to be able to reason about relative configuration of points. And you can only do that if your network in its representation carry directional information. And that's what our method does, whereas EGNN, it doesn't. It only works with invariants and pairwise distances. But if you need to reason about are the bond angles correct and the distance is correct, or like the relative positioning, you really need directional information. So if you incorporate that in our hidden representations, we got like a nice boost in performance and using otherwise the exact same diffusion model. Yeah, so we tried it on equivariant point cloud prediction. I stated before maybe that this method is applicable to point clouds on homogeneous spaces of SEN in general. So also position orientation space. For example, we could treat the bonds as primitives. So a bond has a starting point in a certain direction. And now we can send messages between edges, let's say. And this also adds to expressivity. But maybe another conceptual thing is, well, if you have a surface, we could think of it as a point cloud of normal vectors. And now by sending messages between the normal vectors, you can directly take also curvature of the surface into account. Yeah, and other times you need to predict direction vectors, for example, in this dynamics forecasting. Okay, that's what our method is able to do. And just to show that it also works for 2D, we included superpixel MNIST and got state-of-the-art results on that. This is going to be a one slide. In general framework of message passing, you want to use geometric information, and typically you do that via pairwise attributes. And that's what our paper derives. We derive a full set of pairwise attributes for different cases. If I have a point cloud in position space, and we want to be invariant to rotate translation groups, and obviously the only thing that you can leverage is the pairwise distance. We figured out what does it look like for the group or position orientation space. Remember the set of normal vectors. Then we have actually 4 invariants that we can leverage and nothing more. And there's a nice results by Olver, or in his book at least, on basically that these sets are basically a set of fundamental invariants, meaning that every other invariant could be obtained from this set of invariants. So that really means this is all you need. Yeah, maybe let me jump to the conclusion. So there's a whole bunch of our convolution. So let me skip that in the interest of time. So what I presented was basically a framework for learning geometric representations, which I framed as neural idiograms, like geometric representations of things that could be abstract in principle. And it reaches equivariance beyond just rotations, right? And this is, I think, an important thing. We showed that these representations are more geometrically meaningful relative to the plane vector representations by this classification experiments, and also by showing that we can actually use this in dynamics forecasting, such as in PDEs. What I'm really excited about is now, for me, this feels like, yeah, now we start to develop tools to make the geometry explicit. And it's not that we really do a scene reconstruction, it's just that we learn an abstract representation of the scene. But this abstract representation is grounded in geometry, so it still allows to reason about relative transformations and all. And I think this is interesting, and this is something that our group is going to work on the next coming years. And okay, what is a better way to end the talk is like to show some nice pictures again. And so I want to end with the picture of Picasso. Really, we're going for this ambitious goal of turning image content into a compressed symbolic geometric representation that still preserve the essence of it. And at the same time, and maybe this is a bit of wishful thinking, but I think we are onto something, is that this could provide a solution to the prevalent texture bias, right? That our neural networks tend to focus on pixels, colors, texture, rather than actual shape. And that's why I like to show this Vertumnus picture there. And yeah, maybe, okay, with that, I would like to conclude this talk. And thank you very much.
Thank you so much, Eric, for this exciting talk. I really like what the sentence you said in your slide, like how to explicitly apply geometric reasoning when geometry is only implicit. So it's so exciting, and we can probably take a few questions from the audience, if there's some. Okay, so actually I have a few questions. So from some low-level details to also the high-level ideas. So the first one is that I really like how you apply like local features or like combine local features with equivariance. So I'm wondering like first of all, like is it also possible like I noticed in your work that you're using these local features to better represent like global equivariance on like rotations or transfer like translations. But is it also possible to like combine apply these local features to like local transformations to like study like local equivariance? Like for example, like multi-part objects or deformations kind of thing.
Yeah, this is a great point, and this definitely something that I want to explore next is if we have this encoding, and currently, and this is really early stage work in the sense that our encoding is somewhat naive. We just initialize these latent points on a grid and then move them with gradient descent, this auto decoding principle, to the right locations. But you can imagine that if we spend some time on working out how to do this encoding, which now we use meta learning for, but I'm thinking of more sophisticated or a different approach to this. You can imagine that if you fit this image, here's the ear that one of the latest, let's say it lands there and another one there. But if now we have a different cat and the ear is over there, then you hope at least that this latent moves in that direction. At least you can argue that if this ear is shifted a little bit, yeah, this latent would fit also a little bit. And actually we could steer that in our auto decoding by only updating the geometric information. And so what I'm saying here is that this encoding scheme has a notion of, well, diffeomorphism invariance, right? Or equivariance, in the sense that if this is slightly deformed, then I expect the local point cloud also to be deformed. And yeah, this would be really amazing if we get a hold on, how to properly, well, first of all, define diffeomorphism equivariance, because I don't think you can fully do this, but maybe in a statistical probabilistic sense. And yeah, so yeah, I think we have some notion of local equivariance because each latent is locally responsible for generating the image content.
Yeah, thank you so much for the discussions. Actually, I have a couple more questions, and also we have a question from the audience on Zoom, but probably we're already running into the time for next presentation. So yeah, I guess we have to cut off here. But if you have like more questions to Eric, you can probably email him, I guess. Are you happy about that?
Absolutely. And you can find me on Twitter too. There's several ways to reach out. And please feel free to do so.
Yeah, thank you. Thank you so much. Thank you again.
All right, you're welcome.
So now, following Eric, we have two slide and the first one is going to be lead learning frames for 40 quantile sequence understanding. So actually, a while ago during the break, like someone also discussed with me that like a lot of like works here are discussing about like equivariance of static settings, like static images, static point clouds. So whether there could be some applications or like combinations of equivariance in like dynamic settings, we have like temporal sequences. So now we have to work addressing this aspect.
Okay, so this is the agenda for today. I'll start introducing the task, which I assume many of you may not be familiar with, the task of neuro-weather modeling. And then I'll present two different models that we are working on to solve this problem. And the main messages here is, I think the time is right for applying equivariant neuro-weather models, or applying equivariance and ideas from geometric deep learning to this task. And also, I'll show that it might pay off to work on scaling these equivariant models. So many of us design these new models and only try in small toy problems. I think it's worth putting the effort and trying to scale to real large problems. Right, just to start with the task that we're solving here. So the input here will be the state of the atmosphere. So this is a bunch of physical variables like humidity, pressure, temperature, wind speeds. And we'll have that at several altitudes on the atmosphere. And we can have one snapshot, like a T0, or we can have more than one, like the past up to now. And we want to predict the same variables in the future. It could be, and there are many ways of doing it. It could be predicting in one step the time, the variables like 6 hours, 12 hours, 18 hours, 24 hours ago, or forward, or it could be autoregressive. And one thing that we should notice here is that these inputs could be scalar fields like temperature, or it could be vector fields like the wind speed. So this could be vector fields on the sphere. So this people who like geometric deep learning will love this kind of data. And I think the most common approach from a high level are autoregressive models. So we'll have one or more snapshots as input, and you're predicting a small amount of time forward, and then we iterate the prediction using our predictions as the input to the next step. And since we are in a computer vision conference, I'll relate this to the problem of video generation, or generating a video from a single image, or from a set of frames, like complete the next frames or predict the next frames of the video. And we have really a lot of amazing recent work in this area. And I want to keep this in people's minds. So this is something we might work towards, how to apply these ideas to the neuro-weather modeling task. The main differences here is that our inputs and outputs are not pixels, they're not RGB pixels, they will be spherical, scalar, and vector fields. And also this weather forecasting task has a very strong physics priors, right? We know, well, we don't know exactly, but there are some part of the physics that govern this model is well known, and we could think about using it. And the data set that is most commonly used for this task is called the ERA5, and this is a reanalysis data set. So this data set will come, this is like just the size and the numbers, right? We have accurate data for about since 1979. So this data set has hourly samples since 1979, and the resolution is 0.25 by 0.25 degree, and we have 37 vertical levels and 16 variables sampled over it. I think the most important part of this slide is like this reanalysis. So how do we get this weather data almost continuously all over the globe in a uniform sampling? The answer is we don't, right? We get data from a bunch of weather stations and balloons and scattered non-uniform sampling. And we actually run some simulation models to predict the rest of the state of the globe. Which is kind of a limitation. We'll talk more about this later. And now I'll show some current approaches for this task, and I'll put them in this axis, more learning and more physics. So on the left here, or the right for you, are the models that will take into account the physics and the symmetries, the things we care about. And on the other side, there are some kinds of models that will just do machine learning over the data and don't really care about the underlying structure or symmetries. So the first is the extreme of the physics-based model. There's absolutely no learning. These are the numerical weather models. This is just solving the equations that we know that govern the weather. So this is fluid dynamics, thermodynamics, and the equations come from things like conservation of mass, momentum, and energy. And this is what is running in most weather forecasting systems nowadays. It's changing slowly. People are incorporating more and more in machine learning, but I think it's still the dominant way of predicting the weather. And here on the other extreme, we have this transformers-based model, which will not incorporate any kind of physics or symmetry. They are mostly based on something like a vision transformer, that you split a projection of the atmosphere, we project into a plane, split in patches, pass threads to some linear embedding, and then just have big transformers operating on it. So it's slightly to the right here of the big transformers are the graph neural networks. So here, these models will take into account at least the spherical domain of this data and do message passing. But in the current instantiation of these models, they still cannot handle the vector fields as vector fields. They will treat vector fields as two scalar channels, and there's no relationship as a vector. And they also have to choose between being either rotation invariant by averaging over neighborhoods, or by incorporating, and in that case, if they're rotation invariant, they are not sensitive to patterns of specific orientations, or they work around that limitation by incorporating like edge features or 3D vectors as edge features, and then they lose the actual rotation invariance, and they're not really equivariant. We also talk more about this later. And I want to highlight this very interesting models, the family of models called Neuro-GCM. So this is also very close to the numerical weather models. So what they did here is they implemented the whole numerical weather forecasting model in a differentiable way in JAX. And they have just a very simple shallow neural network to correct this model. So this is very close to a numerical weather model, with this option to fine-tune it or correct it, correct for the factors that we can't really incorporate numerically by training from data and using a neural network. So this is almost all physics, a little bit of machine learning. And the things I'm talking about today are right here in the middle. So I'll talk about spherical CNNs and equivariant GNNs for this task. We don't incorporate any physics, but we incorporate a lot of symmetries. So we care about patterns that appear, vector fields or scalar fields. There's some local patterns that will appear in different orientations, and we want the models to be equivariant to handle those kinds of patterns appropriately. Now we get these kinds of questions a lot. So first, why are we using geometric deep learning in the age of large language models and transformers? The typical answers are, okay, we can leverage the input structure. The structure is on the sphere, so we should take that into account. Because we take into account the symmetries of the data, we also can have data efficiency and improve generalization performance. But this is something that should scare everybody in this room. So the bitter lesson, if you're familiar with this, I think it was a blog post or something, where Rich Sutton is saying that there are a lot of clever people thinking about clever modifications in these models, in putting more bias in the models, and they're almost always trumped by a new model that has a bigger, more capacity and more data or better data will overcome all the interesting things that we try to incorporate in our models. But in particular for this task that we're talking about and other tasks, I have some counter arguments. For example, the weather is data limited. When I talked about the ERA5 data set, we have good data for roughly 50 years. And if we want to double that data, we have to wait 50 years and collect the data to double the amount of data that we have. So this is still hundreds of terabytes of data because it's very finely sampled and there are lots of variables and it's sampled hourly, but it's still limited. And the other point here is this point of fuzzy versus exact symmetries. So when we talk about natural images and CNNs, we talk about translation equivariant, kind of saying that the distribution of RGB patches over natural images is kind of independent of the position of these patches, which is kind of true, but not really. In the case of the weather forecasting here, we have laws of physics as our prior, right? So we know that the physics there are absolute laws of physics that always apply. So we could leverage this better in this case. So this taking that into account should help. Now the question that's why spherical CNN. So this is the first model that I'll talk about. First is, as I said before, to take the domain into account. And this is, I'm showing here what happens if you try to project the sphere into a plane and apply a regular filter like a CNN or some sort of patch-based transformer as those models that I showed before. So we have heavy distortions over the poles that your model will be forced to handle and allocate capacity to handle that. And another interesting thing of the spherical CNNs is this global equivariance to 3D rotations. So here we are projecting this spaceship, this X-wing to a sphere, and these are learned features from the spherical CNN, and we see that they are equivariant to rotation. So as much as we rotate the inputs, the features will follow. And if we take some sort of average, we have an invariant feature approximately due to discretization. And this is very useful for other tasks, not weather. For example, if we're doing shape classification or shape segmentation and the shapes can come in arbitrary orientation, this would be helpful. Or if we're dealing with, for example, molecules, this is another application we have quite good success on. The molecules is the same no matter the frame of reference or no matter how you rotate the atoms, it's still the same molecule, still has the same properties. So we do really want something like 3D, this global 3D equivariance to handle that. But in the weather, we don't really have that, right? The Earth has a specific position in space. We know that the specific relative position and orientation with respect to the sun. There are parts of the Earth that have sea or mountains, and all those things influence weather, and they are in specific positions. So we don't really care about rotating all the data in the atmosphere that we're giving the correct prediction. What we care about is a little bit more subtle. So in this example, I'm showing some patterns that appear repeated in different positions and different orientations. So this is one scalar field, humidity, I think. And we see some sort of patterns that will repeat in different positions and orientations. And if we have localized filters and an equivariant model, the same filters are useful for both kinds of patterns, either for pattern recognition or for generation. So this is why we want equivariance even in these kinds of tasks. And even more so in this case here, I have a vector field. So this is like a wind. And now we have this vector field. So each little curve there is like integrating the vector field a little bit. And we can see that the similar patterns appear and they are rotated with respect to each other. And we would like to not learn this as two independent entities. We like to share the filters that can represent this or produce this. Now, I'll go on a little bit about how the spherical CNNs work. And the main idea here is the idea of group convolution. And to explain this, I will start with the simplest form of convolution. So this is the convolution on the real line. I have a convolution of two functions on R, and we can visualize it as, excuse me, as like a sliding filter computing inner products. And the main idea of group convolutions is to generalize that to a general group. So if you look at these two equations, they look very similar. So on top, we have the normal convolution. We have an integration over the real line. Now, when we're doing convolutions on a group, we're integrating over the group. And the action on the real line is just a coordinate shift. So that's a subtraction here. When we're in the space of groups, this becomes a group action. And one more thing we're going to need is the idea of Fourier series. And again, I will start with the simplest case of Fourier series. So this is a Fourier series of a function on the circle. And this is what most people might be familiar with. We can expand any function on the circle in the sum. So this is countable, right? In a countable number of basis elements that are complex exponentials with their Fourier coefficients. And again, there's a very nice, beautiful theorem that generalizes this idea to compact groups. So the same way you can expand any function on the circle in this basis of complex exponentials, you can expand any function on a compact group on, again, a discrete countable sum of these matrix elements that are related, or they're actually the group representations. So those the linear representations of this compact group. And why did we talk about Fourier series? Because of the convolution theorem, right? So that's another thing that some people might remember. So if we have those functions on the circle, we can compute the convolution between two functions. So the Fourier transform of the convolution is a pointwise multiplication of the Fourier transform of the functions. And luckily, this also applies when we generalize it to compact groups. So we can compute convolution between functions on compact groups by multiplication of their Fourier coefficients. But now, as I said, the Fourier coefficients will be matrices. The matrix elements are the basis, the group representations are the basis, and you can arrange them in matrices. So each Fourier coefficient is a matrix, and the convolution theorem is actually multiplying matrices here. We're talking about compact groups, and the group that is of interest to us is the group that acts on the sphere. So that's the group SO3, is the group of rotations in 3D. And this is what those representations look like. They are matrices of odd size, square matrices of odd size. And if you want to compute the convolution between functions on SO3, we are going to multiply these matrices one by one. So you can see each matrix has one frequency, right? The Fourier series on the circle, each complex exponential has a specific frequency. Here, the frequencies are related to the size of these matrices. The larger the matrices, the higher the frequency, and they are independent. So we multiply them independently, each one of them, to compute the convolution. And this is one way of doing spherical CNNs, is by first you lift the sphere to the group SO3, and you compute all the convolutions on the group SO3. And this was actually what's been done in 2018 by our friends Taco Cohen and Max Welling. The problem with this is that SO3 is a much larger space than the sphere, and those Fourier transforms are very expensive. So our approach will be a little bit different from that, and we have to introduce a little bit of more theory. First is the Fourier series on homogeneous spaces. So the sphere is a homogeneous space of the group. That means the group acts on it transitively. And we can represent the Fourier transform of a function on a homogeneous space of the group, borrowing from the Fourier transform of the group. And what will show up is some sparsity patterns. So those matrices will not be dense anymore. We'll only use some columns and or rows of these matrices. So the white here will be all zeros, and we can represent the homogeneous space since it's a smaller space in the group. That's how the Fourier transform will manifest. And then you can compute convolution the same way, and you can compute convolution between different homogeneous spaces in this way. And depending on these sparsity patterns, your output could be in another homogeneous space, or it could be in the whole group itself. Luckily, this will simplify a lot for the sphere, because when we relate the sphere to the group SO3, we only need one column. So from all those matrices that represent the basis for SO3 and the Fourier coefficients on SO3, only a single column is used to represent the same things on the sphere. And this might be no surprise. So the matrix elements of each one of these columns are exactly the spherical harmonics, right? What else could they be? If you want to expand the spherical function in a basis, the spherical harmonics will show up. But why did you define things in that way? Because now we have a very nice form of convolution on the sphere that is multiplying these matrices that are the sparse representations of SO3. And again, we have different frequencies, and we can multiply these matrices to compute the convolution. And what we will notice very quickly is once you actually go and do this matrix multiplication, imagine f is your function and g is your filter, you notice that you will not use all the elements of your filter. So this could be two arbitrary functions, but the result of the convolution will not use the whole function. It will only actually use this central or one of the components of this Fourier transform is actually the frequency, the m equals 0, if we're talking about spherical harmonics, which is kind of a limitation, because in the spatial domain, if you're only using that single parameter to represent your spherical function, you don't have an arbitrary spherical function. You have axisymmetric spherical function. So these functions, they are constant per latitude. Anyway, this is what we did also in 2018. It is much faster than the SO3 base, but we have this limitation that the filters are kind of symmetric, so it's less expressive than a full-blown model. But we also work around this limitation a couple of years later by leveraging what we call the spin-weighted spherical functions. So this we're introduced in physics to study gravitational waves, and they are complex values function on the sphere where the phase of these complex numbers will change based on rotation. So if you rotate your domain, only the phase of these values will change. So this example here is and the phase changes according to something we call the spin weight. And in this example, I'm showing a function with spin weight 0. So this is exactly a function on the sphere. And so this is no different than what we've been talking about before, right? The magnitude and the phase will rotate as we rotate the function. Once I have a spin 1 function, the magnitude will stay the same as we rotate, but the phase is rotating according to this rotation. And then there's another beautiful theorem that shows that these spin-weighted spherical functions also correspond to some sparsity pattern on these representations on SO3. And it turns out that each spin that we add will add a column to this representation. So when we're dealing only with spherical functions, we only had the middle column here. Now in this example, I have functions with spins 0 and 1, so I have 2 columns. And then when I do the convolution, my filter, instead of having a single parameter, my filter now has 4 parameters. And this filter, this operation is mixing the spins, right? It's mixing spin 0, spin 1. And another nice thing of this idea is that since these are complex valued functions on the sphere, we can see them as vector fields on the sphere. So this is a way to represent vector fields. So we can have filters that are scalar and vector fields, and inputs that are scalar and vector fields, and the convolution will mix both the scalar and vector fields, and crucially, it is equivariant rotations, right? So you can see this, the vectors are rotating the way you would expect, right? This is something that if you try to represent a vector field as 2 channels, 2 scalar channels, you will not get this property, right? And this is what we did also a few years ago in Europe, called the spin-weighted spherical CNNs. So this is all old work. Our most recent iteration of this lining work was called scaling spherical CNNs. And this is where we try to, well, there's a bunch of engineering, but there's also some model modifications. We try to make this bigger and tackle real large problems with this task. And the main result is this figure. So here, these spherical CNNs that I mentioned have orders of magnitude fewer numbers. So the axis here, like the numbers of convolutions in the model, that's a measure of capacity or expressivity, and also the size of the feature maps, because for some tasks like the weather forecasting, we want very high resolution inputs and outputs. So you can see that in both axes, we could scale this model to orders of magnitude larger models than what we had before. And maybe one interesting thing that we also included in this paper is that I think for most equivariant models, there's always this problem, what can we do at nonlinearity, right? Our nonlinearity needs to be equivariant. And there's a lot of research how to do good equivariant nonlinearities. I think both the organizers here have papers working on that. Sean has one too, yeah. And we found one that actually worked pretty well for this particular case, that it's inspired in one paper by Malat's, Stefan Malat's group, that is called the phase collapse. So here, if you have, here what we have are complex fields, very complex valued fields, And we really care about the phase, right? We don't want to break the phase because the phase has to follow that specific property, that has to follow the rotation. So we can do stuff with magnitudes. We can't really touch the phases. And if you have spin 0, we're kind of free to do whatever you want, right? So what we do here is our nonlinearity only updates the spin 0 because that's where we're free to do whatever we want. And it will combine the spin 0 itself plus the magnitude of all the spins, right? So this is very simple, and it turns out to works pretty well in practice. And it's also probably the alternative here would be some sort of gated nonlinearity that some of papers do, that you predict a whole set of new channels to multiply together, right, to get some sort of nonlinear operation. So that makes it much more expensive, right? You're kind of doubling your number of channels everywhere just to compute the nonlinearity. And this, compared to that, this is almost free. Okay, so with this paper, we released a JAX library. So this is, I put a lot of effort optimizing it, different ways of implementing things, seeing which is faster, but I'm sure there's still lots to do there. There's still ways to make this much faster. Given it's in JAX, distributed training is a breeze. So it's very easy to distribute in as many nodes and TPUs and hosts that you want. And we include these operations, these normalization layers, nonlinearities, the things that we need to be particular about when we're building equivariant models. And this enables these problems up to 100 times bigger than before. And this is available for a while. Now let's go back to the weather forecasting and show what these models can do. We implemented this autoregressive spherical CNN for weather forecasting. And this is the size of the task that we're tackling. So this, we're doing 256 by 256 resolution, and we have 78 inputs and outputs as channels. So this follows really closely this the work from Keisler that kind of kicked off this field of numerical weather modeling, and it was a graph neural network. So the architecture also follows in like number of layers, and we do a single round of downsampling here. So you see most of the channels inside the model will be 128 by 128, which is quite large. And this, the delta T here, so we are predicting 6 hours ahead. So every step of the model predicts 6 hours ahead. Then during training, we are predicting up to 72 hours. So we roll up 12 times during training and backpropagate through all of that. And then during inference, we can we can do more, but for the benchmarks, we did up to 10 days. So we train like looking at 3 days of data at a time, but then we can extrapolate because you can just keep calling the model over and over the same inputs, and we did that up to 10 days ahead. And this is one example of kinds of results that we get. So this is humidity, which is one of the most interesting fields because they have very fine patterns that repeat. And here I think we're rolling out up to 5 days. And this is an example of the wing. So this is the vector field prediction that we are integrating into to show this effect here. These are wings predicted by our model. And the color in the background here is the temperature. Right, so this is just a boring table. So I think that the main bottom line here is that we try to keep this model as close as possible to the graph baseline. Number of parameters, training schedule, inputs and outputs, all kind of the same. And we do better here in most, I think all of them, up to 5 days, we do better in all of the measurements, all of the metrics. Once you go to 7 and 10, slightly worse, but that's where the forecast is really bad anyway. So for both models, when they're doing 10 days ahead, it's kind of garbage. So now we speculate. We're very happy with these results. So it seems like it's worth doing it. A fully equivariant model, this models on the sphere. Spherical CNNs for weather seem to work, but why? So we can speculate a little bit. So what is causing these improvements? First is this I want this to be true, to be the reason. That is, our filters are locally equivariant and are directionally aware. So in the graph models, you can have one or the other, and you cannot really have the local equivariance. You can have, well, in the regular graph model, not the equivariant graph models. You have to choose, right? If you want an invariant model, you can only average over neighborhoods, but then it's invariant. You are not directional aware anymore. And the way these models, this current graph neural networks, where the models, the way they achieve this directionality, and they all do that, is by taking the relative position between nodes, like as a 3D vector, and passing that through an MLP, and using that as features. So that then you lose equivariance, right? It's no longer equivariance once you have that. So they cannot reuse the same filters to do pattern recognition or to predict these kinds of patterns here that are circled in red, right? These vector fields. And also they can't handle vector fields. They handle vector fields as these two channels, right? The west and the north channel, and they treat as two independent quantities. But there's another, well, maybe both things are contributing. So in the spherical CNNs, we have our filters are actually have global support. And we, in fact, go through a lot of pain to avoid that. So we have some smoothness in the spectrum to try to enforce the filters to be localized. But still, these are real filters from the 2018 spherical CNNs. And you still see that they extend all the way, right? These filters here on the top. They are, most of the energy is near the poles, but they extend all the way. And the GNNs have a very small receptive field, right? Usually you have one hop, and we are talking about like 256 by 256 graphs. So how many layers do you need of a GNN to take the whole? Is a lot of layers. So they are much more local and have a much smaller receptive field. Let's discuss more small versus large receptive field. So we used to think that we should use more receptive fields, right? So that was the common knowledge, at least for CNNs. We can learn hierarchical representations. It scales really well. We can just have a bunch of layers with theoretic kernels and have really lots of them to cover your receptive field. And this local equivariance property that I was talking about also relies on that. If you have a global filter, there's no local equivariance, right? Because your filter is taking the global. So we actually do need that. The downside is that you need more layers to cover the input, which for CNN is not really a problem because they are so cheap. But for graphs, it's actually a problem because the graph convolutional layers are more expensive. So you don't see graph convolutions with hundreds of layers. The paper that we're comparing with also has 8 layers like we do. And great argument for why using a global receptive field. So the transformers, they don't care about receptive fields, right? The vision transformers, you embed each patch, and the transformer is looking at all patches at the same time. And this seems to be the state of the art in most of the vision tasks. So I think nowadays, global receptive field seems fine. And this is what we actually can get with our spherical filters. I didn't mention here that I also said learnable receptive fields. So by design, they have global support, but since we are learning these filters in the spectral domain, the model can choose to learn a representation such that the filters are smaller, and we actually encourage that. So maybe our models are just learning the right size of a receptive field for the task to leverage the local equivariance, but also take into account the global representation of the problem. Right, and another thing that I used to say a lot, this used to be like a slide saying, yeah, we're still very far of being able to tackle, and there's no way we can go around the complexity, right? So if we compare with CNNs, so B here is the bandwidth, so that's like the related to the resolution, right? Directly related to the resolution. A CNN will be the complexity ordered of the bandwidth squared times the size of the filter square, and that filter is also very small, so this is order of B squared, very cheap. And the Fourier transforms that we need for the filters are a B cube, and this is like orders of magnitude larger, right? It seems like we can never get there. and let's give up. But now, if we talk about transformers again, if you're doing a transformer on all the pixels of your image, that's b to the fourth power, and this is what everybody does. Nobody does it in all the pixels, right? You have some sort of embedding to reduce that dimensionality, but we can have the same for the spherical CNNs, or nothing stop us. So that doesn't seem so bleak anymore, because I think before is okay. There's still some caveats, right? I think there's a lot of engineering we're not talking about the constants here in this complexity. And there is a lot of engineering that we need to make the Fourier transform. And we also need two at every layer. We need the forward convolution and backward. So it's still expensive, but I think it's not that bad as we used to think. Right. The thing is, we need to scale this further. Recall, we applied this to 256, 256, 78 inputs and outputs. And then concurrent work, right? GraphCast is the state-of-the-art graph neural network. When they came, they are using like 50 times larger input. So the resolution is much larger, and they also use many more channels. That means more vertical levels of predictions. So we still have a factor of 50 to scale these models. And that since we have GraphCast now, it motivated us. Can we just find modifications? Can we change GraphCast and use graph equivariant layers and try to see if that has any benefit? And this is how it shows up in our graph, right? They are still like, again, 1 order of magnitude bigger than our biggest models in terms of number of convolutions and size of feature maps. Now let's talk a little bit about graph CNNs or graph neural networks. So this is the most basic type of graphic neural network, the GCN. And this is the one that is doing just averaging over embeddings of the neighborhoods, right? And this model is very simple. And it's actually invariant to rotations, right? If you rotate these patterns, we're just taking averaging or sum of those features. So it's going to be invariant to rotation. And a downside of that is that you cannot tell these two patterns apart, right? They're just rotations of each other. If you're invariant, you cannot tell them apart. This is not what this graph neural networks for weather is doing. They're doing something like this. So they will have these edge features that will be related to the relative position between the nodes. But the way they use those features is, again, by applying an MLP on the 3D coordinates of these relative positions. So it turns out that these models will be able to tell the two patterns apart, but it's not equivariant. So that means for these models, these two patterns are completely different things, and you need to learn different filters to detect or to predict those patterns. And what we're proposing here is equivariant graph neural networks. And the way to do it is introducing different feature types and introducing in our embeddings, instead of being an MLP, will be some equivariant function of these types. So once you introduce these different types, we can have equivariant functions and we can aggregate neighborhoods. And what will happen here is that we will be able to tell these two patterns apart. So you see that the feature in the middle node here, once we apply the transformation, there's a rotation. The vector part of that feature will rotate by the same amount. That means we can't tell the patterns apart. And this is equivariant. That means that the same filters will work for both patterns, and we can detect or predict those patterns in an efficient way. And we're very lucky that this problem is kind of simplified on this sphere, because we can consider only tangent vector fields. So in this case here, since I don't think it pays off to go all the way through 3D vector fields, we could do that too, but the models get much more complicated and more expensive. So for the 2D, we only need to care about the E2, only the group of rotations in the plane, since locally tangent vector fields are on the plane. So our filters are actually quite simple. And I think we can go a great way only considering tangent vector fields. And also, if you look at the inputs and outputs that we want to predict are like wind speeds. And these will be much more prominent on the tangent plane than in the vertical plane. So that also makes sense from a physical sense to use only tangent vector fields. And this is ongoing work. We don't have results yet. So this is being done by Juan Cervinho at UPenn. Okay, so we are getting close to the end. So the takeaways, remind you, I think the time is right for equivariant neural weather models, and it's a very interesting task. Now we have nice benchmarks. We have nice base models that you can build on, and I encourage people to work on this. And also, it's worth putting the effort to scale these models and tackle bigger problems. Some open challenges. So I talked a little bit about the data set, right? That is the reanalysis. So we have scattered data from arbitrary weather stations and weather balloons and points on Earth that are actually passed through a simulation to produce the uniform sampling over the globe. What if we want to use only raw data? If we really want to learn a good weather model, maybe we don't want to tarnish it with the errors of the simulation, of the assumptions of the simulation. Then we'll have a non-uniform sampling on the sphere, and there's a lot of nice theory about non-uniform Fourier transforms if you want to do these things on the spectral domain, or there might be other better ways of handling this. And another thing is that when I said the results, the results 7 to 10 days ahead that we showed here, they're kind of garbage. And there's not much we can do about it. It's kind of we have no hope that we can predict the weather really exactly, that the temperature that's going to be 10 days from now at some point. That means that the models for longer term, they need to be probabilistic. So what we really want is like, what's the worst case scenario? Or we want a range, or we want a distribution that models the weather 10 days ahead. And that brings in all the recent work on generative modeling and how could we apply these, right? Diffusion models, how do we do a diffusion model to predict the scalars and vector fields on the sphere, or language-based models? How do you tokenize and predict the next token to simulate or to predict the weather in a probabilistic way? Okay. Okay, this is the last slide. I just want to say about we're presenting tomorrow. This paper is not related to the weather. It is related to equivariance. So this is, we are doing intrinsic convolutions on mesh to do denoising diffusion to generate textures. So we have this nice work that is one of the first to do this directly on the mesh using intrinsic mesh convolutions in their equivariant to isometries. And that's it. I want to thank all my collaborators. And
thanks, Carlos, so much for the nice talk. And so sorry for interrupting.
Yeah, that's okay.
Really, like, I've been hearing people talking about equivariance and also hearing people talking about scaling up, but it's probably my first time hearing one person talking about both things at the same time. And also, like, I'm so impressed that, like, the things are implemented in JAX. So there are a lot of, like, there are existing libraries of equivariance in PyTorch, probably also TensorFlow, but JAX is also a little bit rare, maybe because you work at Google, I guess.
No, because JAX is great. So I also encourage everybody to move to JAX.
I feel weird, a little bit like over time, so probably we can take one question or maybe not. Okay, yeah, maybe we can take one question from, I think you go. Yeah, sorry.
Thank you for a very nice talk. You mentioned that there was a bit of a gap in feature map resolution for the spin-weighted models compared to the graph cast, maybe it was like Kangu and Fuji. I was just wondering, at comparable resolution, how does
so the results that I showed comparing against Keisler model, those are comparable. So we compared with Keisler was like the first graph neural network tackling this problem seriously. And then we keep everything the same here, the training, resolutions, even number of parameters, number of layers. they're very different models, but as much as we can, we kept it a fair comparison. And then we do better in most of the variables here. All right, thank you.
Thanks again.
In time, well, it is, if you rotate the input, the prediction on the time will be rotated by the same.
Oh, yes. Hi, Nina, can you hear me? Could you unmute yourself? Okay. I'll first give a brief introduction. So now we're gonna have our next invited speaker, Nina Millane. I hope I pronounced her name right. So Nina is an assistant professor at the Electrical and Computer Engineering at UC Santa Barbara. Her lab, the Geometric Intelligence Lab, aims to reveal the geometric signatures of natural and artificial intelligence. And her methodology interests lie at the intersection of geometry, statistics, and computer science. And her application domains are neuroscience and neuroimaging, and also extracting knowledge from data. So let's welcome Nina for her exciting talk.
Thank you very much. Thank you for the introduction, and also thank you for the invitation. I'm very excited to see a workshop dedicated to equivariance in vision at CVPR. So many thanks to the organizers for putting this together. So we are in the Equivision workshop. So I will talk about equivariance and vision. For the equivariance part, I will introduce the notion of hierarchical equivariance, which departs from the classical definition of equivariance and generalizes it. It's very interesting, I think. And for the vision part, I will talk about both computer vision and human vision. So computer vision and natural vision, if you wish, in both artificial brains and natural brains. So that's why the title of this talk is Hierarchical Equivariance in Artificial and Natural Brains. So neuroscience applications. The main question that this talk will tackle is, how do brains, artificial and natural brains, encode information about the world? How do we make sense how our brain encode the world? If we look at the data, if we look at neurons inside the brain, the data may look like this. So on this animation, every row represents a neuron, and we see a white dot for every time this neuron is spiking. So that every row, every neuron has what we call a spike train, which is this succession of spikes through time. And somehow, these spike trains encode information about the world. So in our brain, not only they encode our perception of the world, what we see, what we hear, what we touch or feel, but these spike trains also allow us to plan and act in this world, which is pretty amazing. And the question is, how? How is such vital information encoded in these apparently random trains of neuronal spikes? I'll put it another way, how does our brain organize information? And our brain and brains in general organize information in many ways. And first, they do so spatially. So they are spatially or physically very organized. In this animation, you can see a brain organoid, which is the brain that someone is growing on a chip. And you can see geometric structures in this animation. This is because this brain, this organoid, is growing neural node connection in a very organized way. These geometric structures that are formed by this neuronal connection are definitely not random. I think they are rather beautiful and a little bit mesmerizing. But the question is, what purpose do they serve? Why would a brain grow neuronal connection in this kind of crazy geometric patterns. And there is a field of research that studies this question. We call it neurometry for neuroscience and geometry. And this field looks at the geometric structures that exist both in the physical world, like the geometric structures of the neuronal connections of the brain, but also in data space of the brain, how the data is encoded after the brain has processed it. So we're gonna have a talk on neurometry and how and show how brains use these geometric patterns to encode the structure of the world. We want to understand how brains use geometry to encode the world. Okay, so to understand this, let's look at the structure of the world. Because our world, the 3D world, the world in which we evolve every day, is actually highly structured. And some of this structure, actually a lot of this structure, can be described by the mathematics of groups and group actions. And since we're in the Equivariance workshop, we'll focus on the part of the world that is structured with group actions. So let me show you one example. Consider a fruit fly evolving in the world. And this fruit fly wants or needs to encode the orientation of its head. So we're going to consider the orientation of its head in 2D, in a plane parallel to the floor, say. So the fruit fly wants to encode one angle that belongs to the Lie group SO2 or the group of 2D rotations. How does it do it? Here you have a video that shows how the brain of the fruit fly does it. So you have a fruit fly walking on air, on a little ball in complete darkness. So the fruit fly doesn't see anything, and yet its brain is going to encode its orientation in 2D. There is this structure in the fruit fly brain called the ellipsoid body. It's a ring-shaped structure. And their neurons are going to fire around this structure in a way that encodes the orientation of the fruit fly head. And the neural activity moves along this ring to encode the orientation of the fruit fly head. So even though the fruit fly doesn't see anything, there are groups of neurons that fire when the fruit fly has its head at a definite orientation in 2D space. So in this sense, we can say that the brain of the fruit fly is encoding the structure of the world. And in that sense, it's encoding the Lie group SO2 of 2D rotation that represents all of the possible orientations that this fruit fly can have. So this is a 3D reconstruction of the structure that exists within the brain of the fruit fly. And in the center, you see this ellipsoid body. This is where neurons are encoding the structure SO2, which is pretty fascinating. What's even more fascinating is that this fact actually happens across animals, across organisms, and across substructures of the brain. So the fact that geometric structures in the world become geometric structures in the brain seems to be universal. In the fruit fly, we've seen this ellipsoid body that encodes the heading or the 2D orientation of the head of the fruit fly. So that's the fruit fly, but then in rats, you have another structure, another subset of neurons called the grid cell neurons that encode spatial position. And spatial position, the position in 2D, can be represented by the group R2. And this last example is one of my favorite one. It's in humans, and it shows how our internal ear encode information about the Lie group SO3, or the Lie group of 3D rotation. In that case, how we orient our head, but this time in 3D. So how this one works is that in our inner ear, we have these 3 rings that you can see on the slide. And these rings are hollow. They actually have fluid inside them. And inside these rings, where the fluid is, there is also some hair, some little tiny hairs, so that when the fluid moves, it will displace the hairs, which in turn is going to activate some neurons. And so you're going to have some neurons that activate when fluid moves in one ring. Other neurons are going to activate when fluid moves in another ring, etc. So that together, this group of neurons encodes the 3 directions in which our head can move in 3D space. So together, they encode the group of 3D rotation. So I also find this quite fascinating. Though this is not vision yet, and we're in the Equivision workshop, this is more like spatial navigation, how we orient our head, how we are located in space. So since we're at CVPR in this workshop, the question I want to ask is, what about vision? How is the structure of images now, or visual scenes, encoded in the brains? So now moving to a visual scene, that's, for example, the image of an office. How does the brain encode this? And what are the groups that will be useful for that? So the question we're going to ask are, what is the group structure of visual scenes? Rotations, 2D, 3D. How do they play a role? How do our brains encode this structure? Natural brains. And then can we design artificial networks that exploit this structure? So we're going to see how we do this in 3 parts. First, group structure. In the first part of this talk is going to be about what is the group structure of visual scenes. The second part is we're going to include that group structure in our model of natural vision, our model of the visual cortex. And in the third part, we're going to include one more level of description, which is going to be a hierarchy. So back to this notion of hierarchical equivariance that's in the title of the talk. We're going to talk about hierarchical equivariant models of vision. I should say that this work is based on 2 papers. The first one called Equivariant sparse coding with Christian Schumacher and Bruno Olshausen that has been published in the Conference of Geometric Science of Information. And the second work called Visual Scene Representation with Hierarchical Equivariant sparse coding with a larger team across the University of California, University of California, Santa Barbara, University of California, Berkeley, University of Amsterdam, and New Theory, which is this upcoming AI startup in the Bay Area, which is very exciting. I'd like to give a special shout out to the first author of both papers, Christian Schumacher, which is an admirable scientist and also has made a lot of the visuals that you're seeing on my slides. All right, so jumping in. What is the group structure of visual scenes? Some quick mathematical prerequisites. What is a group? What do I mean mathematically when I say a group? So group is an algebraic description of a set of transformations. For example, if we look at rotations in 2D, a set of 6 rotations as shown on this slide, the 6 rotations shown on this slide would form a group. And we can also give the mathematical definition where a group is a pair, G dot, where G is a set, and dot is the group law that verifies some properties. So that's the group. Now, I've been talking a lot about group action. So what are these? I'm going to introduce the notion of group representation, which is what I mean when I say group action. The group representation is a matrix description of the same set of transformations, or a set of transformation. In our example with the rotations, the same set of transformations. So if we take the 6 rotations that we had before, now each of these rotations is represented by a matrix. Here, the matrix is just a scalar, a complex scalar, but each rotation is represented by a complex scalar. And that's interesting because now that we have this matrix description, we can use the matrix representative of the group elements to act on other objects. Mathematical definition, representation of a group is a pair rho V, where V is a vector space, a rho is a group homomorphism. Basically, we say that G, the group, will act on a space V through this group representation rho. This allows us to define the notion of equivariance and invariance. I know they've been introduced before, but for the sake of completeness, this is equivariance and this is invariance. They describe whether a map phi is equivariant of invariant, meaning how the map maps a transform object, so an object X transformed by an element G, and whether the transformation is conserved, that is equivariant, or whether the transformation disappears, that is invariance. All right, so now that these prerequisites are done, let me talk about the group structure of visual scenes. In an image or visual scene, we have objects, and these objects have properties that can be factorized into the what and the where. So this is an image. It contains an object, which is this little man here. And this object has a property, a shape, it's a little man, that can be factorized into what and where. The what is the fact that this object is a man, and the where is where the man is in this image. So in other words, this image can be decomposed into a part that is invariant to the transformation. I can move the man anywhere I want in the image, it's still a man. And a part that is equivariant to the transformation. If I look at the location of the man, well, this one is changing when the man is moving. So that's a first way where groups enter the picture to describe visual scenes. Now, this factorization is actually hierarchical because we can take our same object, decompose it into the what and the where, but then realize that this object is made of parts. The little man is made out of different body elements that each have a location, maybe even an orientation in space. And then these are made in terms of subparts, etc., etc. So this group structure is actually a hierarchical group structure of parts, of subparts, parts and objects, each of them decompose into the what and the where, the part that is invariant and the part that is equivariant. Which leads us to this notion of hierarchical equivariance and invariance, which generalizes the more traditional notions of equivariance and invariance. And it goes like this. Consider a scene X that decomposes into K objects, X equal object 1 up to object K. And consider now a product group that we denote G tilde, which is a group G that's going to act on the whole scene. And then K copies of the group, each of them is going to act on the different objects. Then we can define a hierarchical action of a group element G tilde that belongs to the product group, and it's written as follows. And this leads us to defining a notion of hierarchical equivariance and hierarchical invariance of a map phi that would act on the scene. So imagine that the map phi just changes the color of the scene, then this will be hierarchically equivariant to a change of orientation of the scene and different objects. I'm just showing the first level here, scenes into objects, but you can continue this logic and go into parts and so on. So that's something that seems to be encoding the structure of visual scenes, yet current models of vision do not exploit this structure. Can we make them exploit this structure? So let me move into equivariant models of vision. This is the traditional model, the original model of vision. It's a model of the visual cortex of animal. It's been developed by Alshausen and Fields in the 1996. And they model vision or perception as an inference problem. So the idea is that the brain has a generative model of the world and that it will invert that generative model in order to perceive. The generative model of the world written by these authors looks like this. It's a generative model with latent variables. Here, I means an image that is decomposed into D components. Each component has a phi I, that is a dictionary element, and an AI, which is the latent variable, which is how much this dictionary element is activated. And that provides a model of the brain because the AI are going to be mapped to activations of individual neurons. So here we would have D neurons. And we want to model, we want that to be an actual model of how the brain encodes images. And so we're going to also include the fact that the brain wants to be energy efficient. We want to include some energy consumption constraints. And these constraints are going to take the form of a prior over the latence variable. So remember, the latence variable are these AIs, which are the activations of the individual neurons. So we don't want the neurons to activate too often. We want the code to be sparse and energy efficient. So we include in this generative model a sparsity-inducing factorial prior over the latent variables, for example, a Laplace prior. And so in this model of the visual cortex, Alshausen and Fields say that vision is an inference problem. Perception is an inference problem. I've rewritten the model here. So how do we see? Well, this is done according to this work through Bayesian inference, which predicts how neurons are going to be activated. And specifically, A, so the vector A of the activation of all of the neurons, is computed as a maximum as posteriori of the posterior distribution of A given an image I. So the model will predict, given an image I as input, how the neurons are activating by predicting this A. This Bayesian inference model can be formulated as a minimization of a L2 loss, which is a similarity term, with the L1 penalty, which is that sparsity penalty that encode efficiency in energy. There are many algorithms that exist to perform this optimization, but one in particular was proposed by the same authors, but almost 10 years later. And it's interesting because this algorithm, which is the last one here, LCA, proposes how the brain does it, how the A's, the neurons that correspond to the different A's, exchange information so that very quickly the A's converge to these maximum as posteriori estimates. So this is the locally competitive algorithm, the LCA, which proposes a dynamics, actually. So here, a dynamics in time of how these A's, the activation of the neurons, activate through time to, in the end, encode the image. On this equation, you can see that there is the U. So the U dot is actually the velocity of U. It's a hidden variable. And the A, which is the activation of the neuron, is some nonlinear function sigma of U. So the dynamics is written in terms of U, but A is really the activation of the neurons. And this inference approach has received a lot of interest because it allows to recover what we call the receptive fields of the neuron. So it has predicted what brains actually do. So what are the V1 receptive fields? Well, if you stick an electrode inside the brain of an animal, record one neuron, and try to see which are the images that these neurons somehow maximally react to, you're gonna find this Gabor-looking function, like these three Gabor-looking images, like the three images you see on the top. And the model proposed by Olshausen and Field allowed to recover exactly the same images that were observed in practice. So which is why it has been part of the reason why it has been celebrated as a model of vision. However, this model does not mirror the group structure of visual scene. So we explained that visual scenes are really organized. They are composed of objects that are composed of parts and subparts, etc. But the problem is that the model that the sparse coding model has proposed does not exploit this structure, in the sense that if an object is moving, then the activation of the different neurons seems to be moving very randomly. And that's not exactly mirroring the group structure of visual scenes. What we would like to do is have a model that exploits this structure. So a model that looks a bit more like this. When the tree or when an object moves in the image, it'd be great if we can model that the neurons activate in a way that makes sense. So this is what we have proposed in our paper on equivariant sparse coding in the visual cortex, where we model perception as a geometric inference problem. So we take the generative model of the original sparse coding model and basically just relabel the dictionary elements, the phi i's, but also the neurons, the AIs, so the activation of the neurons. We relabel them using group elements label, so G. And this leads us to propose a neural circuit that decomposes a scene into the what and the where. Because the phi G that you have here, this dictionary element, encodes not only the what, so the what will be the Gabor function, this vertical bar, but also the where, where this vertical bar is located in space, how it's oriented in space, and then we could encode also its size, its color, etc., etc. And so this leads us to propose this model of equivariant sparse coding, which is equivariant. Both the generative model is equivariant, but also the inference procedure is equivariant. So I've put the definition of equivariance on the top here. If you consider the map phi, that is the generative model that transform the true latents, the A, into an image, then you can show that group action of the true latent gives a group action on the image. So in that sense, the generative model is equivariant. And then if you consider phi, the map, the inference, then this one you can show that it's also equivariant, in the sense that if you change the image, you use a group element to act on the image, you can show that the inferred latents, so the ones that are the results of the inference process of the dynamics, they're going to be transformed by a corresponding group action. So in that sense, both the model and the inference is equivariant. So we have realized our goal of having incorporating group structure in sparse coding, which gives faster but also more realistic inference. Faster, it's because these dynamics, the LCA dynamics, once you write it with group action, you can actually make a group convolution appear in the equation. And this group convolution can make the computation much faster. And more realistic is because if you look at inside the brains, well, you can see that the neurons are actually organized in terms of how they encode location. So you open up the visual cortex and you can take a little slice where neurons that are close together are going to encode elements in the visual field that are close together too. So by labeling the neurons by group elements, we're actually organizing them in the way they're physically organized in the brain. Incorporating group structure in sparse coding gives faster, but also more realistic inference. Though Could we do even better? Which leads me to the last part about the hierarchical equivariant models of vision. Remember the hierarchical group structure of visual scene? We've talked about the group structure of visual scene in the second section, but now I want to talk about the hierarchical group structure of visual scene in this third section. So the fact that the scene is decomposed into objects that are decomposed of parts, decomposed in subparts, and that each object, part, and subpart has a what and a where. The shape it has and where that shape is located, oriented. Could we somehow incorporate this structure into the sparse coding model? Now, there is something called hierarchical sparse coding that has been published in 2020 that incorporates the hierarchical structure of a scene. But yet this model is not equivariant. This more standard hierarchical sparse coding model will lack this geometric information and therefore will be unable to effectively represent the relative configurations or the transformations. So by contrast, we're going to model perception as a hierarchical geometric inference problem. I'm going to show what's the generative model that corresponds to this sparse coding model, and then show what's the inference we propose as a new model of how the brain encodes this hierarchical group structure of visual scenes. For the generative model, we're first going to model the parts that make a scene. So we're going to say that the image I is composed of some parts. And this is basically what we had with equivariant sparse coding. And then we're going to add some levels by saying that the activations that are part of the first level actually themselves decompose into the expression that you can see here. Now that's the generative model. And related to that, we propose an inference model that runs the LCA dynamics, but layer by layer. Now that's interesting because it provides a highly recurrent neural network, but not the type of neural network that we may be most used to, but the neural network that is highly recurrent with some bottom-up and top-down connection and even lateral connection within layers. So a model that's quite different from the strict bottom-up or feed-forward neural networks that we are used to. If you train this hierarchical equivariant sparse coding model, you can recover indeed the hierarchical group structure. So to do that, we took a synthetic data set that we constructed based on this idea of hierarchical group structure. We constructed this data set using parts, object, and scene, where the scenes were composed of different numbers. Here, 1, 1, 3, for example. The objects were the individual numbers, 1 and 3. And then the parts were these little bars that can together form objects. If you run the hierarchical group sparse coding model on this through inference, you can indeed recover the underlying hierarchical structure. So if these are the true dictionary elements, where at the bottom level we have the bar, and then at the next level we have the two objects, we correctly estimate this dictionary element, which is very exciting from an inference procedure, like this whole thing is working. But it's even more exciting because we think that is what is happening in the brain. So let me show you what I mean by that. We do have equivariance and invariance in visual cortex because it is believed that visual cortex is organized in two streams. And this is the so-called two streams hypothesis, which is a model of the neuroprocessing of vision. These two streams are the dorsal pathway on the top and the ventral pathway that you see on the bottom. Now, the dorsal pathway is the part that encodes the where information. And neuroscientists call it the where stream. That's what encodes location, movement, transformation. So the group elements. And by contrast, the ventral pathway is what neuroscientists say encode the shape, the size of the object. So equivariance and invariance seems to be in the visual cortex, where the where stream encodes the equivariant part, and the what stream will encode the invariant part. What about the hierarchy? To find the hierarchy in the visual cortex, let's see where we have impaired hierarchy. So there is this condition that some people have in which they can describe low-level features of objects, but not the higher level features of an object. So they would label the object on the left a rose twig, or the object in the middle a fencer mask. Well, for example, we see that the second one is a tennis racket. So these people can describe the lower level of features, the lower level features of objects. They can even copy the drawings of the objects, but the perception of the object as a whole, the perception of the collection of features is impaired. And on the right of this slide, you have an image of what we think this condition can look like. That is, if you had this condition, that is how you would see the world. So you would be able to recognize individual objects in the world, but wouldn't be able to tell what's the overall structure of the scene, what is happening in this scene. So if hierarchy can be impaired, if you can recognize the what and the where of low-level features, but not really the what and the where of the global scene, then there must be a hierarchy in the visual cortex. And in fact, we find that in higher levels, in higher physical levels of the visual cortex, so V4 as opposed to V1, we have some neurons that react, that spikes when some objects are present. So here you see data for a neuron that reacts every time an image or a drawing of a hand is presented in the visual field. And you can see that we can rotate this hand, even show a drawing of the hand, this neuron will still fire. So that is an indication that this higher level of the hierarchy exists indeed in the visual cortex, and that therefore this hierarchical equivariance model of vision may very well be what's happening in our visual cortex. I'd like to finish on this slide, which is if there are neurons that code for hands, well, maybe there are neurons that code for other high-level principles. And there is this study that showed that there is indeed one neuron in the brain of these participants that was coding for Jennifer Aniston. So these neurons will spike very selectively every time it is shown an image of Jennifer Aniston in different orientation, but would not spike if shown images of other celebrities, or not spiked if shown images of objects, etc. So we are at the top of the hierarchy with neurons spiking for high-level concepts. In conclusion, I hope I showed you how brains use geometry and group actions to encode the structure of the world. In the first section, we've seen how the world, the visual world, is very organized, and that some of this organization can be described with group actions. Then we've seen how we can incorporate this group action framework into a model of vision, more specifically the sparse coding model of vision. And then we went even further by incorporating hierarchical group structure in this sparse coding model of vision. And not only do we get a highly recurrent neural network that can indeed be trained and decompose the world into its elementary components, but even more interestingly and fascinating to me, I think we get a generative model and an inference process that might very well be how our brain encodes information. So brain use geometry to encode the structure of the world, and we're using geometry to describe all of this works quantitatively. That's the end of my talk. I'd like to thank the collaborators, pictures on the left. And if you're interested in all of this, check out both our papers, but also our Python packages. We're maintaining 2 Python packages, one on geometry called geomstats, and the second one on geometry in brains, both artificial and natural, called neurometry. Thank you very much.
Yeah, thank you, Nina, so much for this awesome talk. I guess probably people will have a lot of questions. I'll start with the one on Zoom because this person asked like in the middle of the talk, like pretty early. So the question is, can these relations somehow be connected to a combination of persistent homology and multi-parameter filtration? I think this question was asked like in one of the previous slides about, I think, geometries in the world become geometric structures in the brain, like kind of like some slides over there.
Yeah, I remember seeing this question appearing during the talk, right? So yes, there is a connection with topological data analysis. And actually, that's the first step when you're trying to describe the geometric structure that the data forms once it's processed in brain. So let's say you give an image to an artificial brain, and then you record 100 neurons and how they spike. And maybe you're going to move this image, or maybe this image is a video. And so as time goes, then the neurons are going to have a spiking trajectory. And you can draw a trajectory in what we call neuronal state space, which in our case would be a 100-dimensional space where each vector describes the neurons. And then we have a trajectory of activation in this 100-dimensional state space. And we want to understand the geometry or the structure of this trajectory. And the very first step of such analysis is to ask, what is the topological structure? Is it a ring? Is it a sphere? Is it a torus? And indeed, people use persistence homology. Yeah.
Yeah, thank you for the answer. Do we have other questions from the audience? Probably you can come to the front too. Yeah.
Hello.
Hello.
Yeah, okay, François, University of Copenhagen. Thank you a lot for the talk. There have been quite also other works to try to model at least the visual cortex using notion of fiber bundles and things like that. It seems that they are all always turning around the same things. Would be some nice connections, because I think fiber bundles are also automatically linked to group actions. So
yes,
would it be possible to mix these representations?
Yes, yes, absolutely. And thank you so much for mentioning this. I think maybe the model you have in mind is the model by Petito, where they use, yes?
Yes, yes, especially for the very lower part of the visual cortex.
Yeah, yes, exactly. For V1 in the visual cortex, yes. Where they use sub-Riemannian geometry to model the activation of neurons. And yes, it's very related, and actually it's on our to-do list to merge both. So yes, 100%. Because in this, yeah. Great question.
Yeah, in mathematics, principal bundles are built on group actions.
Exactly. Yes.
And then most of the fiber bundles are associated bundles to these principal bundles. So my guess that there should be some sort of a very clear path to connect the two of them.
Exactly, because even this fiber bundle structure is physically encoded in the brain, where you have these columns of orientation that literally describe the fiber of the fiber bundle. And that's exactly why if you label the neurons by their group elements, then you organize them in a way that is closer to the physical organization they have in the brain. And then the diffusion process across that physical organization can indeed represent the inference that we think is happening. So it's very connected. Yeah, thank you so much for this question.
Yeah, you're welcome.
Thanks. Do we have other questions from the audience? Okay, you can come to the front.
Hi, thank you for the talk. It's been really interesting to know the hierarchical equivariance. And I think it's also interesting because I think in machine learning, we know that machines are good at low-level learning. And then you also mentioned like higher level in geometric is really what I think it's really what humans are good at. And I wonder if you have insights in how these low-level equivariance we learn can contribute to higher level, and how can we use that in this hierarchical sense?
Interesting question. So how the low-level equivariance can, why the low-level equivariance is interesting and how it contributes to this kind of higher-level equivariance. I hope that's the point of your question. Yeah. But I think what's interesting with this hierarchy that is it's efficient in terms of memory storage. So instead of storing or having to encode all the possible configuration of my body, then I can first encode at the higher level how I'm globally oriented, and then encode how each of the parts and subparts are oriented. And I think by decomposing this into a hierarchy, you're able to use by fewer neurons to represent all of the possible combinations. So I think that's how the lower levels and the higher level can play together to have a better representation of all the possible shapes that an articulated object can take.
Thank you. Thanks for your questions. Do we have other questions? Otherwise, we'll conclude Nina's talk here. So thank Nina again for this super exciting talk. I guess it's very inspiring for people, especially who are interested in like getting inspiration from how human perceives the world to building networks that trying to perceive the world in a similar way. So thank you again.
Thank you so much. Thank you for the workshop.
Thanks. And I think now we're gonna have a very short coffee break until 3:45 p.m. And then afterwards, we're gonna have the 2 spotlight talks and also the tutorial on how to get started with building neural networks that are equivariant to geometric transformations. So thanks, everyone.
in the video. Okay. I don't think I can. With the panel? Yes, I found it. Yes. Okay. Today you heard a lot of great talks on equivariance. In this tutorial, the goal is to get you started with equivariant deep learning and how to leverage symmetries in your problems, especially in computer vision applications. We're going to start the tutorial with some theory discussing groups, then the notion of equivariance and invariance more rigorously, and then we will build equivariant layers that have been built over the past years with techniques from using the group theory. Then we will move on to building an equivariant point encoder using these layers, and then we will discuss more applications that are in general in the fields of computer vision, robotics, etc. And we will close the talk with limitations and open questions on equivariant deep learning. Okay, so let's start. The symmetries are in general very elusive but very important in many tasks. And there is a question on how do they manifest. For example, when you see an image and you want to do an object detection, you might want to detect the humans in any pose, in any scale, in any position in the image. When you see, for example, a point cloud and you want to reconstruct it into an occupance function, for example, these points might, because we provide the coordinate system for the points, this might be numerically different if the chairs are translated, for example, but in the eyes of the network, we want them to be reconstructed consistently, independent of their orientation or their scale, for example. In pick and place tasks, as you saw before, you might want to pick or place an object independent of its pose and independent of the pose of the gripper. And also, as you saw in the Hagai Maron's talk, for example, when you encode an object, a neural object, like in a neural audience field, when you encode it in a neural network, this neural network might have symmetries that describe the same object. So, for example, if you permute these matrices in a very particular way, you encode the same object, although if you unroll the vector, it might seem different. So this creates a permutation symmetry. And you need to build like methods that process those objects consistently. So this idea of equivariance is not new. It has been explored in the past, even before deep learning. I would say that one of the most successful applications is for key point matching, where the idea is that you have, for example, you need to match these planes, the books, that they undergo a projective transformation, and you want to build features that are equivariant with respect to those transformations so that you can match consistently. And one good approach was building like features that are called shift features that were scale invariant and also rotation and translation invariant, with the idea that you build expressive, distinctive features to match the key points, descriptive to be robust to noise by describing the neighborhoods, but also invariant to some transformations. Also, this idea of steerability that we will see also later appearing in equivariance has been explored even before the shift features, where the idea is to build filters that when they are transformed, they can be expressed in a basis of some standard filters by only transforming the coefficients of those. And since convolution is linear, if the filters have this property, the convolved signal will also have this property. In the deep learning region, I would say that one of the most successful applications, embedding like the translational symmetry in neural networks, which gave rise to convolutional neural networks. The LeNet, for example, or Neocogretron even before that. So let's discuss a little bit about what is a symmetry. A symmetry is a transformation that leaves an object invariant. For example, if you see the picture on the left, you see a very symmetric type of flower that if you rotate by 36/8 degrees, you will get the same picture. And also if you flip on an axis, you would get the same picture. And this is called, this set of transformations form a large, like a family that is called D8. Also, when you see, for example, mathematicians have studied those symmetries for many years. And for example, there are patterns that are 2D but repeat in 1D. These are called freeze patterns, where you see here the footsteps with what is called a glide reflection transformation. When the patterns repeat in 2 dimensionals, this is called the wallpaper transformations, and in 3D, it's the crystallographic groups or transformations. And the goal of the mathematician is to classify all those different structures up to isometries. And you would hear words like, you can only choose among 17 wallpapers because there are only 17 types, different types of these kind of groups. Moreover, these asymmetries appear in continuous settings, especially when you put coordinate systems on objects that you want to be treated the same. For example, these 2 chairs are just roto-translated versions of themselves, but in a coordinate system, they appear numerically very different. And you would like, and the symmetry now is the asymmetry with respect to the coordinate system, that if you transform one chair to the other, if you transform one chair, you would consider this to be a symmetry because it describes, even though numerically it appears different in the coordinate system, it describes the same chair. Formally, a transformation group, first, what is a group? It is a set with a binary operation that is closed. If you take 2 group elements, 2 transformations, and you apply them one after another, you get another transformation. And you need to satisfy some properties like this binary operation needs to satisfy associativity. Then there should be an identity element with respect to this transformation, to this operation, and there needs to be an inverse element for every element. If you see, for example, in this figure, you will see that you get this f rotated 4 times, you get back to some f. And if you flip, for example, then you can start composing transformations that still give you a closed set of symmetries. And I want to pinpoint that the group elements are the arrows, the transformation, not actually the configurations, but there is a bijection, as you can see, between those 2. A transformation group now, in our context, is like a group. This set G contains a group of transformations, and the operation, the binary operation, is just composition. These like ideas have been studied a lot in mathematics, and you can find, for example, in group theory, the mathematician studies the properties of the groups themselves and how they're structured. In representation theory, you study how these objects act on other objects, for example, vector spaces that we will discuss. And in harmonic analysis, there is also like this notion of a generalized Fourier theory on how to put a basis on functions on those groups. So let's discuss a little bit about how a group acts on other objects. And the group can act on many different ways, but what is an action? An action needs to satisfy some properties. For example, when you get a group element and your set X, if you apply the identity element, then you shouldn't move the object. The object should stay the same. Moreover, the most important is that if you apply like a transformation H on your object X, and then apply transformation G, then this should be the same as applying this single element G composed with H, this single transformation on your element X. And this single group G can act on many different objects. For example, when you see in the main figure, in the second line, you will see that there's a scalar field where you rotate it by 90 degrees. And in order to find the corresponding color, you need to just rotate the grid. But for example, on a vector field, like in the first row, not only do you rotate the grid, but if you carefully see, you also need to rotate the arrows themselves. Another example is, for example, the Gaussian function that if you rotate it, you create another Gaussian function with a rotated, the mean rotated. This is rotated as a vector, but just applying a matrix on the vector, and a rotated covariance matrix. But this now action is completely different because it's both on the left and on the right. So a group can act on many different ways on different objects. Moreover, if you select like your objects in a particular like representation, you might give rise to more symmetries, to a different group of symmetries. For example, if you try to describe a mesh, a triangle mesh, with the coordinates, then when you rotate, the coordinates will appear different. So you have a symmetry under all these transformations if you want to be consistent on the description of the mesh. But alternatively, if you see on the top, you might give an intrinsic representation. For example, you might give the angles or the dihedral angle and the ratio between the vertical and the side. And after a rotation, this would be exactly the same description. The object does not see any rotation because it's not described in the extrinsic space. So there is this idea of acting on different objects. And in particular, what we're interested in machine learning is acting on vector spaces. And to repeat what an action is under this structure, an action needs to first satisfy, keep the property of the vector space. This means that whenever you get a group element, you will act on the vector space and return an element again on the vector space by keeping the structure of the vector space with additivity and scaling. But moreover, you need to satisfy another property, which is that when you apply this transformation on some object, some single transformation that's composed with G and H, then this needs to be the same as doing the transformation of your vector by first applying H and then applying G with the same representation. And this gives a property on the vector space that is more than just adding and scaling vectors. This gives a property of geometric vectors because now you can act with a group too. For example, you can rotate your vectors. If your group is if your space is finite dimensional, this is just described by n invertible matrices, like the rotation matrix that we saw before. And why do we care about linear actions? Even though we might have in some cases like spheres or different spaces, in machine learning, we usually have functions on those objects. And even though the action on the base space might appear nonlinear, the action on the function space is still linear. For example, the left regular representation that is induced by this action on the base space, dot here, which is not linear because it's on the sphere, the total representation on the function is still linear. For example, if you applied it on the sum of two functions, you will get the sum of the functions computed on the rotated domain. And the thing that to keep about linear representations and in general representation theory is that it is important to know that these structures have been studied a lot by mathematicians, and that those representations, in particular the linear representations, can be decomposed into smaller representations. So even if some representation appears to be very complicated, it's actually structured from smaller representations that leave some spaces invariant in your vector space. For example, your vector space might be decomposed into one-dimensional vector spaces, but these representations would keep some of those spaces invariant, depending on the group. And we will use that in order to solve the equivariance constraints later to maximize the degrees of freedom. So that's how we utilize the representation theory and especially the decomposition in order to separate the independent degrees of freedom. And let's jump to an example, for example, in the rotation group. Is this a symmetry group is the question, like the symmetries that we saw before. And it is a symmetry if you, for example, take the vector space R3 and impose a norm, for example, the Euclidean norm and a basis, and you ask what are the symmetries that would preserve, the transformation that would preserve the norm, the handedness of the basis, and the vector space structure. This would give rise to this group called SO3, which contains 3x3 rotation matrices that have this property that rho transpose times rho is the identity, and that the determinant is equal to 1. And as we saw, you can rotate many objects using SO3. For example, you can rotate the coordinate of this blue point 3 by just applying the rotation matrix. or you can rotate the whole inertial matrix by applying the rotation left and right, or you can rotate the color function by rotating the grid, or you can rotate a function that is a vector function on the points, where not only do you rotate the grid, but you also need to rotate the vectors themselves on the points. All these are different actions of SO3, but we know that SO3 is compact. And for compact groups, as we saw in the previous theorem, they can be decomposed into some basic representations. So all these actions can be decomposed into basic representations. That will be the building blocks for all those types of representations. And this has been studied a lot, and I will be very brief into that. The irreducible representations of SO3 are called Wigner D matrices. There is a sequence of matrices that are 1 by 1, 3 by 3 matrices, 5 by 5, 7 by 7, and all in general the odd numbers that have this particular form. For every element, for example, if you parameterize your SO3 group with Euler angles alpha, beta, and gamma, then you create those matrices that are 12 plus 1 by 12 plus 1 that have its entry has this particular form that involves also the spherical harmonics, which is a basis for functions on the sphere. Utilizing this irreducible, you can decompose any linear representation. For example, the inertial transformation that you saw that is applied from left and from the right can be decomposed into those after a change of basis. This inertial matrix that is 3 by 3 after vectorization is a 9-dimensional vector, can be decomposed into some representation that is 1-dimensional and irreducible, a representation that is 3-dimensional, and a representation that is 5-dimensional. All in all, giving 9 degrees as the vector, the unrolled vector. And this means that there are, by this decomposition, you can see that you take this vector space, you unfold it, and after some change of basis, some of the subspaces will be acted only by particular representations and will be unaffected by the other representations. So that's how you decompose in general a group action into the irreducible representations. And let's jump now into what is invariance and what is equivariance. This characterizes the functions. So let's say that you have a group G, and you have your input space X and an action on that, an output space Y and an action on that. And let's say that for your instance, small x, you first apply a transformation and then you apply a function, or you apply a function on the original input. Then invariance would mean that these outputs should be the same for every action, for every group element G. For example, a point cloud classification could have this property. Differently, equivariance for different tasks would mean, if you see the commutative diagram on the right, would mean that if you apply first the transformation, creating a new object x prime, and then you apply the function, for example, segmentation mask, or you first apply the function and then you apply the transformation of the output, which could be different, then if those two end up in the same output, then we say that the function is equivariant. And equivariance has many nice properties. For example, the standard technique is to impose the equivariance on linear layers by restricting the degrees of freedom and then designing ad hoc nonlinearities and composing them this way in order to get equivariance from end to end in a deep learning setting. Equivariance can be seen as an inductive bias also because it's a form of constraint on the function space. And the way that we use representation theory, as we discussed before, is in order to decompose these constraints into the independent ones. And the reason is to maximize the remaining degrees of freedom. One note about invariance is that even though our function might be invariant, equivariance is still relevant because premature invariance might cause some troubles. For example, if you take an invariant representation of just the eyes, the nose, and the mouth, by losing the relative pose between them, these two structures would appear the same, but we know that the left structure describes the face, where the right one is not so clear that describes the face. Okay, so what's the story so far? How should you think about your symmetries? You should think about this trifecta of group, space, and action. What is my group of symmetries? What is my input space and my input action? And what is my output space and my output action? For example, if you get a point cloud that you might want to be consistent when you, for example, reconstruct into an occupancy function, you might want to be consistent with respect to the transformation of the points. For example, the transformation could be a rototranslation in 3D, and also in the input of the network, you might give a different ordering of the points themselves. In that sense, the input space, the group is this SE3 cross SN. The input space is a point cloud, and it's transformed by left by a permutation and then a translation. And in the output space, you have occupancy functions that when you apply this action of the group, you get, again, the occupancy function of the rototranslated grid point. Okay, so we have the group, the space, and the action. We would like to build layers that are parametric and process this input plus action and produces an output plus action, aka equivariant layers. Before that, there is a question on why to build equivariance in our networks. And there is this idea that equivariance will give us some benefits, for example, statistical benefits because of the smaller hypothesis space. As we said, there is a constraint, equivariance constrains the hypothesis space of all the possible functions. So with a smaller hypothesis space, we need fewer samples to learn the best function inside that. And also we have fewer parameters, which means due to weight sharing, but keeping the same expressivity. This gives rise to smaller networks. Moreover, if you want to impose exactly the constraints, because you have, for example, a physical law that you need to be satisfied exactly, or you have some safety constraints that you need to be guaranteed, this exact constraint satisfaction of equivariance gives rise to robustness and feasibility. And one last important thing is that this constraint is imposed even outside the training distribution. We didn't even discuss the training distribution. This is a constraint on the function space, independent on the input, as far as the input could be acted by some group action. And you can also see that via, for example, this image on the left, that when you rotate it, when you process it in order to produce some features, and then you rotate it, those features are stable, and the output is predictable. So this gives us stability in the intermediate layers, and we can utilize that for extra inductive bias. As you saw in some of the talks before, there is an alternative to equivariance that at least that goes hand in hand with equivariance, which is canonicalization. And canonicalization is an invariant description of the input that will later be processed by network. There is some things that are important to note for canonicalization. For example, when you try to canonicalize these two planes that are very close to themselves, like they're only small rotated copies of themselves, by predicting the pose, for example, this is a very non-smooth function because a small rotation to the right, and you would canonicalize into this object in the middle, but the left rotation would be a very large number of the pose. So this would give rise to a very steep function if you try to predict the pose in order to canonicalize. Moreover, by doing it in a naive way, you don't get a robustness to noise. For example, if you take this point cloud and you do a PCA in order to find some canonical coordinates, if you add a little bit of noise that could be seen here in the end of the plane wing, and you do a PCA on that, then the canonical object might be very different. So these two objects now will appear in the input of the network as very different objects, and they will be processed in a very different way from the network. So doing some canonicalization is important to do it correctly in some sense. And again, providing like an intrinsic description of a shape, for example, in this mesh, you do kernels on the surface of the mesh, creates a question on what would you do if you had, for example, two meshes and the relative poses mattered, as we saw with the Picasso problem, where the relative poses of the eyes and the nose and the mouth really mattered for the problem. So in some sense, when you want to create a canonical object, this is not something trivial and involves learning this canonical mapping. But if we learn this canonical mapping, which is an invariant input representation, then this definitely involves equivariant deep networks. So even canonicalization can utilize equivariant deep networks. There is also the other alternative of doing data augmentations. And this has some advantages. For example, you get more than groups. You get data-dependent transformations that might be crops, jitter, small noise. And also, you don't have a very specific architecture. You don't change anything in the architecture in order to do the data augmentation. And one more benefit is that it's imposed from input to output, not per layer as equivariance is done. However, it's very costly during training, especially for larger groups, because you need to show all the transformations. It's not exactly imposed as with equivariance. For example, if you have physical rules, as we said, or safety constraints. And most importantly, it's not imposed outside the training set. So you only get guarantees, not even guarantees, but even like it's promoted to be, the data promotes the model to be equivariant, but not outside the training set. So you don't know what would happen in the during inference. One small note is that usually this inductive bias of equivariance goes hand in hand with locality and hierarchy, but this synergy is not well studied, yet. And this is like the blueprint of this paper called this white paper called Geometric Deep Learning by Bankel-Bernstein. So using these ideas, let's now build some equivariant layers that people have done during these past years. And in order to do that, we would need to, again, think about the trifecta, group, space, action. What is my group? Does it have some structure? Is, for example, continuous or discrete group? What is my space? Is this a vector space? Is it a functional space? And what is my action? Is it linear? Is it reducible? Okay, this slide. Okay, so let's say that we have a function on a matrix group G. This function is from a finite dimensional space to a finite dimensional space. And we get two representations. The input representation is a matrix that is n by n. The output representation is a matrix that is m by m. Then an equivariant linear layer, which would be described by W, would be equivariant if it satisfied this equation. W times ρ1 of G equals ρ2 of G times W. But this is a constraint for all group elements G. In particular, if this group was a continuous group, this would be uncountably infinite constraints. However, we can utilize notions like from representation theory in order to decompose this representations and actually find the independent degrees of freedom. For example, there is like this very important and very elementary lemma that's called Schur's lemma that says that if the representations are irreducibles, then they're either the same and the matrix is just a multiplication of the identity, or they are not the same and then there is no matrix that satisfies this equation. And although this might seem simple, this idea might give rise to a very popular architecture. For example, with SO3 rotations, you get your matrix, because this is an irreducible representation, you get your matrix to be just, instead of a 3x3 with 9 parameters, you get only one parameter, which is A times the identity transformation. That means that when you get a point cloud, for example, instead of 3n by 3n matrix, you only get an n by n matrix that scales the points and linearly mixes them, but not in a way that you can mix them differently in coordinates x, y, and z. You can only scale them uniformly in x, y, and z. And that is because when you rotate them, the x, y, and z loses the meaning, because the x coordinate could turn into a y coordinate, etc. That simple idea gave rise to a very popular architecture that is called vector neurons, designed by our organizer. Extending on that, there is this paper that is on more general MLP, on general MLPs with general groups, general matrix groups, that rewrites this equation into a eigenvalue equation. And then they utilize representation theory to decompose this representation into blocks that are independent. And then they utilize the generators in order to reduce the number of equations into those that are really linearly independent, because not all equations are linearly independent. For example, if you try to impose that on, for example, the Lie group SO2, which describes the 2D rotations, instead of a 2x2 matrix with 4 degrees of freedom, you would get a matrix that has 2 degrees of freedom, one in the radial component and one in the tangential component. If you try to impose it on discrete groups, then you don't need to solve it everywhere in the group, especially for larger groups. This is very important. You only need to solve it for the generators. And this is the relevant equation. That is a linear equation because all these are matrices. So you can do that via SVD, which is like what this paper proposes. And for example, if you solve it in closed form, you will see that when you get a signal that is 4-dimensional, instead of having a matrix that is 16 with 16 degrees of freedom, you get a matrix with only 4 degrees of freedom. This, when the group action is like a circular translation, this is the form of a convolutional in 2D. This is like a kernel that is rotated, is circularly rotated, and will be multiplied with a 4-dimensional vector. Now, if you increase your symmetries and you also permit more than circular rotation, you also permit transpositions, then you have even more constraints. And this is the group of permutations of 4 elements. And that is very relevant to, for example, graph neural networks, where the degrees of freedom now reduced from 16 to 2, where you can only have a self loop, a weight for your own value, and a single weight for all your neighbors, because your neighbors are interchangeable. So you get 2 degrees of freedom. Okay, so something happened here. What about now functions on the, we discussed about finite dimensional spaces, but what about functions on those spaces? I want to be brief on that because we need to move fast into the application. But if we have functions, we need to find equivariant linear operators between functions on the group. Then that gives rise to the group convolutions. It's a generalization of the standard translational convolution, where you have your function on the group and your kernel on the group. And instead of just translating, you also do all the possible rotations like a template matching. This might create, this is like very, this type of equivariant layers is very like, goes hand in hand with standard nonlinearities. You don't need to create ad hoc nonlinearities, as we will see later for other types of equivariant layers. And it's also a very unified perspective for many groups, the group convolution layers. And for some groups that involve translation, they can also be implemented fast using the standard convolution after some smart indexing. The only problem is that this integral cannot be exactly computed, so it needs some sampling in order to do that. And smart sampling really makes a difference in the performance. And the same goes for now functions that are from the space, like this Mona Lisa image, from the space to the group. When you have such functions, then this gives rise, the equivariant linear layers would give rise to what is called a lifting convolution, where your function is on the space, let's say Mona Lisa, your kernel is again on the space, but the output, after you integrate all the roto-translated versions of the kernel, you get a function that is on the group, for example, in SE2 group. And if you see here on the right with the image, you see, like, for example, the group that is the semi-direct product of the translations and 4 possible rotations. You get your kernel, which is like the I kernel that tries to detect ties, and you pass it through the Mona Lisas using like only the translation. And then you do that 4 times by applying this group C4 on the kernel itself. So all the rotated possible copies of the kernel, and you do the convolution again. So you create four different channels with all the rotated copies of the kernel. And if you now rotate, if you say, for example, during inference, the rotated version of Mona Lisa, then you would still apply the same 4 kernels, but now you would still detect the eyes as you did before, but not in the first channel. You would detect them in the second channel. So that function is still equivariant, but with a different group action. Okay, and the problem with these layers is that they create like a memory overhead. That is one negative aspect that needs to be addressed. That while the function is on the space, the output function, as you can see, are 4 copies, and for larger groups, it will be multiple copies, where you don't have extra degrees of freedom. The degrees of freedom are the same, it's the kernel, but you do a very large feature space, which creates like a memory overhead. This idea of doing a lifting convolution to go to the group space, then doing a regular group convolution, as we saw before, to go between group spaces, and then doing a projection operator like a max pooling on the group, is the idea that gave rise and popularity to the equivariant deep learning, which is the regular GCNNs from Taco Cohen in 2016. The last architecture that I want to stay a little bit on is the functions between the original space, where you change the feature, the dimensionality of the feature field. For example, when you get such function, you need to again specify how do the functions transform. And if we have the rototranslation group again, then you could transform such functions by if you view it as a scalar field, you only need to do the transformation of the grid. But again, as we said, if you have a vector field, you need to also post-multiply with the rotation of the vectors themselves, not only the transformation of the grid. This unified perspective can be described by these types of actions. And if you try to find all continuous equivariant linear operators on those, this will look like a convolution, but with a restricted kernel. And the restriction of the kernel is of this form. And this is called the steerability constraint. Now, if you try to solve it, for example, for the roto-translations in 2 dimensions, depending on the input and output representation, you get a kernel that is unrestricted in the radial part, but is very restricted in the angular part. And you can see the form of the kernel here in this figure, where, for example, if this difference between the input transformation is 0, you get an isotropic kernel. If this is 1, you get this type of circular harmonic type of kernels. And this idea also was also explored first in the harmonic networks by Daniel Worrell in 2016. Now, this type of networks that are called steerable equivariant CNNs, they can be exact even for continuous groups. For example, here with the continuous rotations, you can impose the transformation exactly if you can solve this constraint. And this is the negative part, that if you can solve this constraint depends on the complexity of the group itself. Moreover, you need to design ad hoc nonlinearities for those type of networks, which people have done in the past. And if we have a connection between what we discussed before, the convolutions that are lifting, and the steerable convolution that we discuss now, there is a connection between those things via the Fourier transformation. Of course, the spaces can be more general than as we said, than vector spaces. For example, these ideas have been explored with spherical images from sphere to sphere, functions on sphere to functions on sphere, or functions on sphere to the group itself. And these are described, a general theory is described in this paper, a general theory of equivariance and on homogeneous spaces. There are even more types of equivariant layers, for example, those that parameterize in the Lie algebra. And there are even more general spaces, for example, solved beyond vector spaces on Riemannian manifolds or on the ray space with a projective group, and very recently in Clifford algebras. And now we will move into the part of the talk that is on the applications.
Thanks, Ivan.
Yeah, so after we have seen some theory, we will go and see how, like a simple case study of how we can build an equivariant point encoder. So yeah, the point encoder gets a set of points as input, and we will assume that they also get a set of corresponding vector features. And first we need to identify what's the symmetries that we want our model to have. So the output feature, which we will concentrate on the feature of, let's say, the central point. What's the properties that we want this output to have? And before we go into the more complicated rotation equivariant, we can see some other properties that feel more natural. And the first one is just translation equivariance. So if we just translate the input point cloud, we want the output to be also a translated point cloud and the feature to remain the same. Another property is that we want the output to be independent of the indexing that we chose for our points. So if we just permute the indices, we want the output to remain the same, but be for the corresponding permuted index. So let's say these are the symmetries that we are aiming for, and we can see that we can achieve them with a simple message passing network. So let's say first we have the points and we have the edges of the point of interest, which is the central point, with the neighbors. We just compute the messages using a function that takes as input the features of the neighbor, the point, and the relative position of the neighbor to the point. So this difference here. So after we compute these messages with any function phi here, we can aggregate them with a simple summation to get the aggregated message. And then if we pass the aggregated message through another general function that can be any MLP or whatever function of choice, we get the output, which is this blue vector feature. So here, if we translate the input, because these functions that compute the intermediate messages don't see the translation because they get inputs of that are invariant to this transformation that we want to be equivariant in. So if we translate, we just get the same message. And also, if we permute, we don't get now the same messages because the indices of the messages change. So we can get a different order. But the final aggregation that we do, it's independent of the order because we just add everything. So we get again the same output. So here we just achieved translation and permutation equivariance without getting any constraint on the models that we want to use. So this phi that computes the message and phi f that aggregates, it's not constrained. It can be any MLP. And we got that because the input representation to these functions are invariances to the transformations that we want. So this is close to canonicalization. So these functions always see a canonical image of the input, which doesn't change if we transform it. Now, let's say we want to do the rotational equivariance, and we want the output, sorry, to rotate when we rotate the input. Here, again, we can use the same canonicalization techniques that were described previously, but again, it has a lot of problems that we need to address, like the problems Evangelos mentioned. So let's describe what we want our network to do. We want, given the input, if we pass it through the function, to have this commutative diagram, which we can also express as by just replacing the order of the vector in the output. So if we rotate the input, we pass it through the model, and we rotate back the output, we want to get to the initial positions. So if we try this to our model, to our message passing model, and we input the rotated version, we can see suddenly that the messages that we compute are rotated. And this happens because now the transformation that we apply is not does not change the input that this function see. So the inputs are not invariant to the transformation we are now interested in. And we can see that even if we rotate back, again, the output, after we rotate the input and we rotate it back, it's not the same as the original output, which is our goal. So this way we get the constraint for the equivariant message passing, which is that we want now our message function, when the input is rotated and we get the output and we rotate it back, to be exactly the same as the initial unrotated output of the unrotated input. Yeah, so we get this equivariant message passing and the constraint that we need to put in our models. And we can see that these constraints can also apply it in a different setting where we specify more about what are these functions. And instead of having a general function that takes the input features and the difference between the points, we say that our message now is just the feature of the neighbor multiplied by W, which is a function of the edge. And then if we also simplify the aggregation function to a simple summation, we get the steerable convolution. And if we translate also the constraints that we arrived for the equivariant message passing, we get the constraints for the steerable convolutional kernels, which can be seen as taking the input point cloud, looking the positions in the learned kernel that correspond to the relative positions of the neighbors, and putting this position as messages, and then just do the aggregation. So we see that in this setting, for the equivariant message passing, we need to constrain the message functions, and in the steerable convolution, we need to constrain the kernel. And how we can do that, which is the question. So how we can impose the equivariance? One simple way, if we assume that the vectors that we are interested in are 3D vectors, is using vector neurons. So here the input is not just a vector, but it has m stacked 3D vectors all together. And the linear layer that we are interested in is just a left multiplication with a W matrix, a learned W matrix. And we can see that the implementation is pretty much applying the linear layer to the input vector. Just we need to take care of applying the layer to the correct dimension of the input, which is, for example, here, the second dimension, because we have buds, the stacked channels, the extra 3 dimensions, which correspond to the vectors, and yeah, the points that we have. Now that this is like a simple way to solve the problem, but we can also go to a more general way, which is using steerable convolutions. And we will show an example of SO3 steerable convolution. So as we described before, what we want to achieve here is to find these kernels W that satisfy this constraint. And yeah, this is a linear constraint on the W's. And a solution to this is described with this equation, where you see that the W's, if they are expressed as a basis of Y here are the harmonics and Q are the Clebsch-Gordan coefficients, but you can think of it as a static basis. You don't need to learn anything. And then the only degree of freedom is to learn this phi function that takes as input only the norm of the x, which, as you can see, the x is the relative position with the neighbor. So for the SO3 steerable convolutions, we want to implement these kernels that it's some learned coefficients for a known basis, which involves the harmonics and the Clebsch-Gordon. And this can be intimidating, but there are pre-implemented libraries, and especially you can do it with the E3NN library. And we have an example showing how it can be done. So this kernel pretty much wants to do the Clebsch-Gordon tensor product between the harmonics and the input feature. So how we do that? First of all, you can see, yeah, as we said, we can use the implementation of E3NN, and you can see that we can describe our input representation, which is more general than what we had before. So we can say, for example, this is a syntax thing, but this input means that we have 5 scalar features and 5 vector features. And in the output, we want 5 scalar features and 1 vector feature. So yeah, we can describe any combination of features. And after we describe that, we can just let the pre-implemented tensor product to do the rest of the job, which just need as input the representations that we want the input and the output to have. And also it needs the weights that you can see here, because yeah, we want to compute these weights using an MLP that takes a single input, which is the norm, and outputs for each J here, the corresponding weight that we learn. So after we defined this module, we can just do a forward pass by taking the spherical harmonics of the edge difference, which is the relative position between the neighbors, passing the norm of the relative position to the learned network to compute the weights, and then putting everything together in the tensor product. So this example was mainly to show that although the SO3 steerable convolutional kernels, the solutions seem intimidating, there are implementations that you can use, easily use to implement it in your work if you are interested. Yeah, but again, it's more complicated than the other example of vector neurons, but you get the additional expressivity of defining the type of input and output representations that you want. So the other part of the puzzle is the nonlinearities, that because until now we just described the linear layers, and a general recipe used in a lot of works for nonlinearities, giving the input features to disentanglement into an invariant part and an equivariant part. So if we apply the nonlinearities on the invariant part, we can do whatever we want, and then we can combine it with the equivariant part. For example, as Carlos mentioned in the previous talk, the equivariant part can be the phase, and the invariant part can be the magnitude. So we don't want to mess up with the phase because this gives us the orientation. But in the invariant features, we are free to apply the nonlinearities that we want. So this is an example of getting the input vector features, passing them through a norm, for example, to get the invariant part, apply a nonlinearity here, which can be a ReLU, and multiply it with the equivariant feature, which can be the initial vector or a normalized one. But yeah, it's up to choice. And this is the nonlinearity using the tensor field networks. But we can do more complicated stuff. For example, we can produce two equivariant vectors and get the dot product to get an invariant one, pass it through RLU, and as long as we don't mess the equivariant part of the features, and we just let them interact with the nonlinearity with a simple multiplication, you can do a lot of different combinations to get the nonlinearity. So this diagram is used in vector neurons, but in general, it's still an open area of research of finding a nonlinearity that works well, it's stable, and yeah, it's still something the community is searching for. And we can apply this same recipe of getting the dot product between equivariant features to achieve a nonlinearity and invariant feature, to also implement attention in the layers that we described before. So you can imagine that we have a message passing function, and we introduce here the query feature, which also is derived from an equivariant function that takes as input only the feature of the node we are interested in. And if we take the dot product and apply the softmax, we can use this softmax to aggregate the new messages that originally we aggregated with a simple sum, but aggregate them weighted by this softmax from the dot product. So we get this typical attention module where you have the query. This would be the value. The query, the key, you take the dot product and you just aggregate the values using the weighted attention score for each message. And we can see, because assuming, yeah, it's here, yeah. Okay.
Can you do taxi?
I think I can. Thank you. So assuming that the messages are computed by equivariant functions, although we rotate the input, the dot products that we get are invariant to that. So we can use this property to implement the attention, because you can see here the softmax will give the same result regardless of whether the input is the original form or rotated. And we get just the rotation on the value part, which will, goes out of the sum. So in the end, what we get is just the original output, fj prime, rotated by the output rotation. So we can achieve the equivariant property. So this general attention layer and the previous message passing ones are a way to achieve equivariance, but as Evangelos mentioned, another way similar to that is going through group convolutions. So here we saw an example of how to do that, but for simplicity, we just use the discrete group of 90-degree rotation. So how we go with the group convolution, we take the input and we rotate the input, or you can see it as the dual of rotating the kernel. But here for visual, we rotate the input to get with all the elements of the group. So we get 4 rotated versions of the input. And then we multiply with a kernel that it's unconstrained to get an output. And the size of the output is the size of the elements of the group. So how we get equivariance here? Let's say we get a rotated version by 90 degrees. If we do the same operation and we rotate the rotated version, we will get the new inputs. And you can notice here, because the group is cyclic, this rotated input correspond to the second, to the G1 rotation of the first. And the result of this is that if we apply the same rotation of all the group elements, we will get just a shifted image of the initial input. And then if we apply again the same kernel convolution, we will get the output, but it will be just cyclically shifted to the top. So a rotation on the input corresponds to a cycle shift in the output, corresponding to the cycle nature of the group that we are interested for, which is the C4. So this is another way to implement an equivariant model, and it has the additional benefits that now the kernel psi can be unconstrained. And also we can use, because it is unconstrained and the output is just a function of the group, so it doesn't have the vector nature that we didn't want to mess up before. We can use any nonlinearities that we want and still have this equivariant property. So here this transformation can also be more complicated forward passes. And we still get the property because the input is just a symmetric shift. So the output will also be a symmetric shift. But the negative, which we didn't have with the message passing version, is that now we have, for a simple group of 90-degree rotation, we have 4 copies of the input. So you can imagine that the memory constraints in our network are, the memory requirements are higher than doing an equivariant message passing, but we get the simplicity from being able to do any transformation after we leave to the group. This point encoder can be applied to many applications. So we can use it for point cloud processing, which is a natural one, but also can be applied to computational chemistry, for example, to compute the properties of the molecule, which should not depend on the orientation of the molecule, and also in robotic manipulation, similar to a talk we saw before in one of the spotlights, where we want the features that describe the object to rotate accordingly to the transformation we apply to the object we want to manipulate. And also, if we go back to 2D images, we want, and we consider the problem of 2D key point extraction, we want a transformation on the input to not affect the matches that we have. So this is also the concept of the shift features, but also it's still an area of open research. So this is from 2023. And if we go to the image domain where we have a fixed grid, we can also do more efficient computations, because now the edge difference that before can be anything, it's predefined. And there is also a nice library, ESCNN, that can be used to achieve equivariance on grids, predefined grids. But here you can see a property of this last example, that both pair of images rotate. So we don't have a single rotation, but we have both pairs rotate differently, and we want the output to be independent of the rotations. So this property is beyond the typical equivariant definition, and pretty much is what we saw before as bi-equivariant. So in the typical equivariant, we have a rotation of the input that corresponds to a rotation of the output. But what if both pairs of the input rotate with different transformations? How we can connect the two puzzles? What we need to do is first to get the blue puzzle to the initial position, then do the original transformation that we had before, and then do another transformation, which is the TY, the T yellow, to arrive to the final, to the final connection of the puzzle. And if we compose all these transformations together, we can see that we are interested on a new transformation where the individual transformations of the input are applied to the left and to the right of the initial prediction that we had. And this is the bi-equivariant property. And this is a more general property than the original equivariance, where we have a single transformation acting, but we can still use the equivariant encoders that we have built to achieve this. And an easy solution is extract equivariant features and then multiply them together to get a bi-equivariant feature. And if we assume that these features are 3D vectors, we can also retrieve a rotation by applying a procrustes. And by this operation, you can see that we also get the bi-equivariance property that we want, because if we rotate the inputs with different transformations, when we construct the bi-equivariant feature, the one transformation appears on the left and the other on the right. So since the SVD doesn't affect this property of the input, we will get, doing a procrustes, we will get a rotation, which is the original rotation with the corresponding transformation on the left and the right. And these applications can be, this bi-equivariance property can be used on point cloud registration, where we want to register the point clouds independent of the rotation of the input. It can be used in pick and place, which was the paper that was presented before in the spotlight. And also it can be used in protein docking. It has been used in protein docking, where we want to find how protein docks with a ligand independent of the original position of the molecules. And this bi-equivariance also goes beyond rotation, so we can also see it in the permutation equivariance, where we have, when we consider matrices, that we apply permutation both on the columns and the rows, and we want the output to also permute by applying the corresponding permutations on the columns and the rows. And in Hartford et al., they showed that they can achieve this bi-equivariance property with a linear layer, and they saw an example of the general solution that this linear layer has. And this also can be applied to different applications, but I will go a little faster due to time. But you can see that, let's say we have input images and point tracks. We can permute both the images and the point tracks, and we want the output to be the corresponding one to the transformation we applied. But also if we consider weight matrices from neural networks, we want, when we permute both the input and the output columns, the network to also see that these two matrices after the permutation and before are the same, because it's just permuting the ordering of the channels. So it is the same network. And yeah. This can be applied for processing weight matrices of neural networks, for either changing the networks or regressing some property that the network has. So to close up, we can go through some limitations that we currently have in the space of equivariant deep learning. The first one is the increased computational and memory requirements, which is especially for the group convolutional layers. But there are a lot of works that try to mitigate that. So for example, we have the EPN, equivariant point network, that suggests a separable convolution that does a convolution on the R3 space and then a convolution on the rotation space, and it combines them to do the whole SE3 convolution. Then we have E2PN, which also proposes to do the convolution on the sphere instead of the whole SE3. And also the recent paper from Eric that presented in the morning, that they defined an equivalent classes that different weights of the network are parts of, and these equivalent classes and the networks that are contained in them share weights, so they can also achieve equivariance in this way. Another limitation can be that solving the constraint that we saw before for example, for the SO3 steerable kernel can be non-trivial. So some recent works on that are the implicit convolutional kernels. So instead of trying to solve the constraint of the kernel, we just use an equivariant MLP to implicitly learn the kernel. So for its input, X, and let's say whatever latent we are interested, instead of having a closed solution for the kernel, we pass the input through a equivariant MLP. And because it's pointwise, so we don't need a kernel on the whole space, it can be more easily modeled, and we can restrain it to satisfy the constraint that we are interested in. Finally, in a lot of tasks, while in an ideal scenario, the tasks have symmetries, in practice and when we measure when we measure the properties that we want, these symmetries are not followed and they break. And this can have a detrimental effect if we want to model non-symmetric data with a equivariant model, because it cannot process the extra degree of freedom. And on that end, there are recent work of introducing approximate equivariant networks that allow for the model to partially follow the equivariant constraint, but also have a degree of freedom for breaking the constraint. For example, instead of a typical convolution, we can have an extra learned W that breaks the constraint of equivariance. And they have used Wang and Tal, they have used these networks to also show that in physical systems, for different scale of the system, you can see different degrees of symmetries and equivariance. For example, in the flow, if you scale down, the flow should be equivariant, so don't depend on the orientation. But in the large scale, actually the flow is not equivariant because it depends on boundary conditions that create this equivariant error. So for the larger scales, modeling the flow with an equivariant method can reduce the performance. And they show that allowing the network to break equivariance in some parts of the network actually improves the performance. And this has also been shown more theoretically by Petracci and Trivedi. Yeah. So the last limitation that we can discuss, and it's an open question, is that in general, in the whole conference, everyone tries to scale the models with more data. So yeah, how we can do that with equivariant models that require more computational constraints, and do we need this model in the current setting of big data? I think the answer should be yes, as we have seen throughout the day, but yeah, it's an open question that we need to discuss as a community. So I will close with some resources of some useful libraries for implementing equivariant network, and also some books and courses that you can refer to as a starting point. Thank you.
Thank you again for this nice tutorial. I guess next time when people have a summary of resources, our workshop should be added to the list.
Yeah.
And yeah, I think our program is done here today. Thank everyone for coming to our workshop. We cover a lot of exciting topics, and we also have this tutorial introducing the how to get started with equivariance. When I was listening to the tutorial, it reminds me of my undergrad when I was doing mathematics. So at the time, we were required to take a physics class. So I was asking people what physics is easier, and they were saying, oh, probably quantum mechanics because that is only linear algebra. So and then I started to realize when people try to pretend something's easy to model, they say, oh, it's linear algebra. Although this one is a joke, but I think it's actually very fascinating that the simplest thing in the world, that is the linear transformations, can actually model so many fascinating phenomena in the real world, like in physics or even in some logical structures. And also, it's very lucky for us that for computer science, nowadays we have TPUs, GPUs, the processor units are actually very good at computing linear algebra or the tensors. So there are actually a lot of opportunities for us to use computational algorithms nowadays to model the geometric structures in the real world. And also, as mentioned, in the end, there are still a lot of challenges, like data from the real world, they have noises and their computation costs. And we still need to tackle all these things in our future works. And finally, probably let Pastor say a couple of words to conclude our next speech.
Before I thank the organizers, I would like to point your attention to the CP is organizing a workshop at RSS, Symmetry. Vanderlop and Gilstrand and others organized the workshop at Neuro, Nina who gave the invited talk, organized the workshop, the TAG, the Neuro-geometric workshop at ICML, and there's also the Symmetry representation workshop at Neuro, right? So I think the main bulk of the